Hello everyone and welcome to Unacademy classes. My name is Abhishek Mishra and in this class we are going to do a marathon revision of casting, forming and welding. So let's do that. But before doing that, let me just inform you about some of the benefits of Unacademy, and I will also give a brief introduction of what I'm going to teach, how I'm going to teach, and things like that. So, without further ado, let's start the class. So, let me first of all drink water. So, let's start the class. I will open the chat, the YouTube chat, so that I can interact with you. And feel free to ask questions because I think if you are preparing here in online, mainly in Unacademy, the educators are very much going to help you. So make sure that you are asking questions, clearing your doubts and things like that. So the stream is working fine. Let's start the class. So I have secured All India rank of 662 in GATE 2020. I have completed my MTech in 2019 from IIT BHU Varanasi, and I've got a good teaching experience of 2 years in mechanical engineering subjects. Some of my interests are photo editing, video editing, cricket, football, and I like all sorts of games. So I will be taking this class mainly in English, and I will also be discussing some of the tips and tricks along our whole this revision, and we will do all the questions quickly. I will not do every question fully because this is a revision class. Some of the questions I will do, and some of the questions I will just tell you how it is going to be done, because a lot of questions that I have are similar. So I don't think that doing each and every question in this long class is going to be very worth it, because we are going to, I think this class will go on for about 4 hours or so. So let's start the class. So if you have not followed me yet, then you can follow me on unacademy.com. Here is the link. So just go to the link, that is unacademy.com slash at the rate 19abmi dash or hyphen 9136. Then you can follow me there. And what are the benefits of following me there and why you should follow me there? First of all, my whole schedule will be visible to you. I am taking unacademy.com classes which are very much different. Some classes are similar, so if you are missing some live class, then you can visit there and see if I am going to take that YouTube live class there or not, so that you can attend it. And also there are some exclusive classes that I'm taking there, so you can check that out also. So the classes that I'm taking, I am teaching you from the notes. So that notes you can freely download by visiting my classes on the Unacademy's app and website. So follow me there to receive all these benefits, to watch classes for free. I am taking free classes there, so I think you can obviously come there and see what type of classes happens in the website and app of Unacademy. So here is the code ABHIMI that you can use and get this Unacademy classes for free, and also some of the notes that you can get for free. So this code is very important, so just note it down somewhere or remember this ABHIMI in all capital letters. And not only my class, you can also watch some other educators class also. So I think this is very much a important code that will come in handy, so it is better to keep it somewhere, to note it somewhere. And I will also tell you some other benefits of this code. And if you have not downloaded the Unacademy app, the time is now to download it. The app has all the things that is important and necessary for your online preparation. For example, I will just point out some of the things that this app has that you can use for your online preparation. First of all, live classes then recorded classes, archived classes, this uh, quiz competitions, test series, all those things are there in the Unacademy app for you to look into. And also the traditional test series which you have to give for preparation of GATE is also there in the Unacademy's app. So Unacademy app is a complete package, and I think you can totally download it and check it out for yourself. And after downloading it, if you have already downloaded it, or after downloading it, make sure that you are exploring the app properly, because this app has a lot of things and which needs to be explored. For example, you can see how to get notified whenever an educator posts something, so that you can be aware of that thing. So this is the Unacademy app, and I think you now can get the benefit of, and now can know the benefit of this app and check it out for yourself. So there are some multiple batches starting: evolve, ascend, and here is the code again that you can use. Same code which you were I said you to use for this free classes and notes. You can use the same code for free notes, and for this 10% discount to subscribe or to buy this batches which are going to start from the 28th, that is today. And for mechanical they are starting from today. And why it is important for you to join this batches, because evolve and ascend are two batches for gate 2022 and 2023. And if you are planning to give those exams, then it is better that you start your preparation now, because if you are starting it at the very end, or at the, for example, after 4 or 5 months, you will find that the courses are very much to look into, to study. And what you will do, you will try to study for longer hours and prepare in a fashion which is not recommended. So to prepare in a calm manner by also doing a lot of other things, you should start as early as you can, because this will make you feel like the course is not that long. So again, one more thing: you have live classes and archived or recorded classes, and it is always recommended for you to attend live classes, because recorded classes don't have that interaction which is very important. And when you are attending a class live, you can clear doubts there only. And I think you can clear doubts better than in your online offline class, because in online class you have that comment section where you can post comments, and the educator will look into it and answer your questions. And sometimes what happens in traditional offline classes, you can't do that due to just disturbing the class, and also due to some other reasons, like due to just not getting this courage to ask question. But in the comment section you can totally do that. So let me be just so these are the batches that are going to start. And I hope, and these are the things that I think I missed. So somehow what I did, I posted a code image and forgot to just hide it, so it was blocking this PPT. And now you can think these were the slides that I was discussing about. So you can follow me. This was the link that I was talking: unacademy.com/@19abmi dash 9136. And this is the code that I was talking about, and you should also have seen that code in that code image that was before shown. And Unacademy app, I also talked about it, and this was the batches that I was talking. And now what you will get when you subscribe to Unacademy: you will get daily live classes, live test and quizzes, structured courses, unlimited access of content. So the most important thing here again is daily live classes, because as I was discussing, you can ask your doubts, answer poll all while the class is going on. And live tests and quizzes are also there for you to evaluate your preparation with giving them regularly, and also after that you will receive detailed analysis, which I think is very important, because some of the students keeps on asking, they keep on asking that, sir, how much test we should give, or how many times a day we should give a test, or how many or if we should give test from this side or this side. So the most important thing is to not give a lot of test, but to give test and then analyze your performance. Because if you are, even if you are giving, for example, 20 test series or 10 full length test series, and then you are preparing, seeing what is your mistakes, working on them, seeing where you are keeping taking more time and working on them, then it will be more beneficial than you just giving 40-50 test series and not looking into what mistakes you are making, not improving them. So I think this analysis is very important, and Unacademy is providing you analysis after test series in a very detailed manner, which will help you a lot and which will make this whole thing of giving test series well worth it. And next we have structured courses. So all the courses that are taught in Unacademy are structured in line with the syllabus. So they it is done so that you can prepare best in Unacademy's website or Unacademy's YouTube channel or Unacademy's app. And structured courses are also there to help you study in a manner which will create a rhythm, or which will make you study in a progressive manner. Why progressive manner? Because if you are a new student, then you want to study in such a manner that first of all your basics are cleared, then you will be taken to a normal level, then advanced level. So this is always there in Unacademy courses, that progressive approach is followed, and unlimited access of content will be provided. So if you are subscribing, then you will get all this content like test series, quiz competition, small quizzes, recorded session, archive sessions, and the live classes, notes. So all this you will get for one subscription, and here are the subscription prices. And as you can see, this subscription price, so let me just, so as you can see, this subscription price right here are very reasonable. And so the subscription prices are very reasonable for the amount of content that you are getting. And no cost EMI is available on 6 months and above subscription plan. The code is there which you can use to get this in discounted prices. And here are the discounted prices of these subscriptions. And the discounted prices here are only going to be available to you when you use this code ABHIMI. So if you are using this code, then only you can get this discounted prices. So before visiting this Unacademy website, make sure that you are having this code with you, so that you can just provide the code and get this 10% off and get the Unacademy subscription for the least possible price. And the best plans to go for are 12, 18 or 24 months plan. Why? Because they are having a lot of discount. As you can see here, the discounts offered in this apps, or sorry, this plans are, the subscription plans are very much more than the rest of the plans. And if you are not sure, then you can go with 1 month's plan or 3 months plan, and after that extend it if you are feeling like it. And also I would like to point it out here, this is plus type subscription, so a classroom type experience will be provided to you for this price. And that experience will mean that a lot of students will be studying in the same class live with you. They will be discussing in the comment section with you, and you can also interact with the class, and also you can answer polls and see if you are able to compete with the rest of the students or not. And this Unacademy prices that is shown in the screen, I think it is better that you subscribe for 12 months even if you are preparing for GATE 2021, because you will have to prepare for the interviews for the other exams like BARC, ISRO, for other PSU exams and stuffs like that. So I think it is very better, and also for MTech. So to have the resources available to you for this least possible price, it is better that you think for the future and this go with 12, 18 or 24 months plan. So new iconic subscription prices are also shown in the screen. What is iconic subscription? It is for those students who need more assistance. So personalized coach, personalized test series analysis and study material and things like that. And the same code you can use to get 10% off here. And these are the prices, again very reasonable. And here are the plus and iconic subscription benefits and the code that you can use to get this 10% off. And don't forget to use this code. I am pointing this out again and again because it is that important. You are easily going to miss a lot if you don't enter this code. So just note it down somewhere, all in capital letters, and use it and get the benefit of the Unacademy that is providing you. And just subscribe and start preparation. And again, this time the best route or best approach to prepare is to join an academy and start doing revision classes, because a lot of classes currently that are going on in Unacademy are crash courses and revision classes. So I think you will get your money's worth by subscribing to these classes, and also by seeing that this Unacademy classes that you are subscribing right now, a lot of, as I have told, revision and crash courses are going on. So you can do those classes, revise, and then come and give your test that is available on the Unacademy's website or app, and follow this approach again, that is revision classes, test, and also you should see what mistakes you are making and learn from them. So follow this thing in the last few weeks to make your preparation very better. So that will be it. Now let's start our today's revision. So first we will start with casting, and we will do a very quick revision since we have a lot to cover. So casting is a process in which molten liquid metal is allowed to solidify in a predefined mold cavity, and we will look into each steps of casting so that you can properly understand what this definition means. Again, in this process we are having a molten metal and we are pouring it in a cavity that is predefined according to which shape or size we need, and then we are allowing it to solidify so that the solidified material that is obtained is our finished product. The steps are pattern making, core making, making mold cavity, then melting and pouring, then finishing. So these steps, just remember the names here, and we will look into each of this step, and also we will study the things that are going to be very crucial for your GATE examination. But the first step is pattern making, then we make core, then we make mold cavity, then we pour the liquid metal, and after that we do the finishing process by removing the extra materials, and hence we obtain the final casting. So this is a casting system with the primary and secondary cavities. So this cavity right here, this cavity right here is your primary cavity, because this is in shape of, so this is your primary cavity because this is in the shape which you require your final product to be in. And rest of the cavity are secondary cavity, which is there for, so this rest of the cavity is secondary cavity. And why we are using this secondary cavity, why we are making it? We are making the secondary cavity so that the molten metal reaches properly the primary cavity, and also the casting take place in a proper manner. So this secondary cavity is the gating system, that is rest of the part after or rest of the part from the primary cavity, secondary cavity, things like pouring basin, sprue, runner, riser, which helps in this molten metal to reach the primary cavity is our secondary cavity, and we will look into each of these terms in detail as we move forward. But right now, look, when you have obtained this final casting, you will see the metal has solidified. The molten metal, you will pour it from here, as you know. So the molten metal which you have poured will solidify. So this molten metal will solidify and form this. So after solidification, it will look like this, and you can see this two are the secondary cavities which are also solidified and still attached to our casting. So we have to remove this. So we will remove this with the finishing operation we will do. We will do process like fettling and all those things to clean it off. And final casting will be, as I have told, it will be in the shape of primary casting or primary cavity. So this is your mold box, and as you can see, you have a cope and drag here. The upper part will be called cope and the bottom part will be called drag. And what is mold box? Mold box is a box inside which you are making cavity. And how you are making cavity, we will look into it. But see here that you have two boxes, and in both the two boxes you are seeing cavity. And this cavity, inside this you are also here putting cores to make hollow structure, and the final casting that is obtained from the cavities or from the system here is shown on the right side of the screen. The first is from bronze and the second one is from aluminium, but they are both obtained from the cope and drag that is shown in the screen on the left side. But also notice here that the cores, what is core? Since this is a revision class, so I will just be very quick. Core is used to make holes or internal hollow structures, and you can see that the image, the final finished product image that is shown on the right side in the screen is having the internal hollow structures. So that is possible by the use of core, and as you can see where the cores are used, there are holes. So I hope this is clear to you. So let's move forward. And yes, this is the thing that I was talking about: mold box, cope, drag, and the line which is dividing them is parting line. And if your casting is a little bit complex, you can also use cheek, which is the middle part or middle box between this cope and drag. So casting process, quickly we will see this real life example and see what the processes are, so that when we discuss about casting, we have this very image of what casting looks like, what it functions like. So first of all, we have pattern, which is set in drag with gating system parts. So drag box, inside it we are keeping pattern, and there are gating system parts also. Then what we will do, we will make cavity. How we will make cavity? We will hand pack the sand around the pattern, and then we will do this ramming so that the mold cavity achieves this dimensional stability, and a proper dimensionally stable cavity is obtained after we have removed the pattern. But before removing the pattern, what we are doing, we are striking off the drag, and this is done by a straight striking rod. And then we are having this drag ready for the cope, which is the top part of the mold box. So cope is again prepared similarly. Here you can see a riser and a sprue, that is gating system parts, with the pattern of our casting that is put in the core here, or not core, cope here. So again we are doing this ramming operation, and after ramming we are doing venting, that is we are creating holes so that the casting does not become porous and the gases are allowed to escape, which are generated during this casting process. So this is very important, venting. And if venting is not provided properly, gas defects can be obtained due to porosity. And then we are just drawing out the pattern or removing the pattern from this cope and drag. And as you can see, very carefully we are removing it. After the pattern is completely drawn out, you will be left with cavity, which is what we desire, and this cavity will be in the shape of pattern. And then what we will do, we will set up core. Where we have to set up core? We have to set up core in the place where we have to create internal hollow structure. So whatever thing that we are going to get from this casting process that we are looking in right now, we will get that thing with internal hollow structure, and you will look that it has internal hollow structure when I will show you the finished product. So this is scope and drag both ready for closing, and you can also see core there. And next we are just clamping them together so that we can properly pour the liquid metal and there is no misplacing of the scope and drag. And pouring of molten metal is now done. From the pouring basin it will flow through sprue, and then it will pass through this runner and then enter the primary cavity, and then we will get the finished product after solidification. So the finished product after cleaning and all those finishing, we will obtain this finished pump housing casting. And as you can see, it also has the hollow structure due to the use of core, and that is what a casting process looks like. And I hope you just get an idea, or you just revised what it looks like. So let's move forward. So now we will look into some examples of casting process. Door handles, which are very small and very light, and then you have locks also, then outer casing or housing for motor pumps, wheels of many car, gas turbine blades. Gas turbine blades, by the way, are manufactured using this investment casting. We will look into it. And then we have gold ornaments, dentures or false teeth, hollow cylindrical pipes, pulleys, etc. Casting is also heavily used in toy industry to make parts such as toy cars, planes, etc. But one thing that also here we use casting process to make, that is not written here, is machine beds. So machine tool beds is also manufactured or is also prepared using this casting process. So as you can see, machine beds are very large and also they are very heavy, and door handles on the other hand are lightweight and small. So casting process has this advantage of creating either this low weight small few grams objects, and also to create this thousands of kilogram high or large heavy objects. So this is one of the benefits or advantages of casting that you can just remember. And now we will look into microstructure of a casting. So this casting microstructure is having the better, or you can say the best mechanical properties in whole structure of a casting will be found at the center direction or center region. Why? Because there you are getting coarse equiax grains, and as we move away from the center towards the wall, so first of all let's discuss what is near the wall. So near the wall you are getting this fine equiax grains, and the layer in which this fine and equiax grains are there in the casting microstructure is called chill layer. Why chill layer? Because solidification will occur at a सबसे you can say सबसे पहले यहाँ पर हो रहा है this solidification. What I just said is that solidification will occur first in this region which is chill layer. Why? Because here the heat transfer rate will be very high, because here the mold wall which is having room temperature or something like that, and also we will have the molten metal which is having very high temperature, and therefore the heat transfer will occur towards the wall, and the region near the wall will solidify fastest, and the region at the center will solidify last. So therefore coarse grains in the center, fine grains in the region near the wall, which is chill layer. In between the these two regions we will find columnar dendritic grains, and these grains are formed in the direction as you can see, which are mainly dictated by the heat transfer direction, and heat transfer will take place from the center towards the wall in all directions. So this is one question that we will quickly do. During solidification process of a, or during solidification of a pure molten metal, the grains in casting near the mold wall are. So the grains in casting near the mold wall, as we have seen, they are fine and they are not ordered, they are randomly oriented. Here the orientation of them is not in any order, they are randomly oriented. So B is the correct answer to this question. So now let's move forward and pouring temperature. So this is a very quick note. Pouring temperature will be melting point plus degree of superheat, which is 100 degree to 250 degree. Why we are giving this extra temperature, that is degree of superheat? We are providing this so that molten metal fills the mold cavity fully and not solidify soon. If we are only giving melting point, then what will happen after your molten metal has been poured, you will get that it is solidifying and it is losing temperature, and hence if only melting point is provided, it can solidify sooner than your whole filling is completed. So we will take care of that by providing some extra temperature that is around 100 degree to 250 degree, and it is called degree of superheat. Now what is a pattern? So pattern is a replica of a final casting to be produced with some allowances. And why we are using pattern is because we are going to make cavities, okay, and that cavities are made with the help of pattern. So that is why the pattern is important in this casting process. Because of this line, last line, pattern is used to make cavities, and that cavities are the places where we are going to pour liquid metals, and that cavities should be of very proper and exact shape that we desire. Because if the shape and size of that cavities are different, then we cannot get the proper casting or final casting with dimensional accuracy. So we need pattern to be very precisely made, and then we will need the cavities to be very precisely made, and that will be taken care of by providing some allowances, which are some modifications to compensate for some of these things that we will discuss. But again, pattern is a replica, not exact replica, just a replica of final casting to be produced with some modifications or allowances. And here the point that is written with the star sign is pattern and part that are to be made are not same. So they are not same. Why? Because pattern again is just the replica of casting with some modification. So that modification means that it will not be 100% same with the final casting that we are obtaining. So allowances that we are giving to pattern are, first of all, shrinkage allowance or contraction allowance. Then we have draft or taper allowance. Then machining or finishing allowance, shake or wrapping allowance, distortion or camber allowance. Let's look into this distortion allowance and shrinkage allowance and other ones individually. So first allowance that we have to look into is shrinkage allowance. I will quickly go through them, but before going through this what this allowance actually is, there are three types of shrinkages that will happen when you pour the liquid metal and when it is solidifying and coming in equilibrium with the room temperature after solidification. So first shrinkage is liquid shrinkage, then we have solidification shrinkage, then solid shrinkage. The first two shrinkages that we encounter, or the metal encounters, is liquid and solidification shrinkages. And this shrinkage means that the metal will shrink, it will contract. So that contraction or shrinkage that is happening when the metal is liquid, or that is happening when the phase change process is going on, is compensated by riser. And the other shrinkage that is happening when the metal has become solid after phase change, and now that solid metal will be getting its temperature reduced because it is not at the equilibrium or not in equilibrium with the room temperature. When at the point C, when metal has become this solid, it is still having this what we can say, it is still having this high temperature which needs to be coming in equilibrium with the mold box or with the room temperature, so that the this shrinkages or this heat transfer can stop. So that last shrinkage that is happening when the metal has become solid is solid shrinkage, and this shrinkage is compensated by doing modification in pattern or providing some allowance to pattern, and that allowance is shrinkage allowance. So here you can see AB is where liquid shrinkage is going to happen, and BC is where solidification shrinkage is going to happen, and CD is where solid shrinkage is going to happen. So from A to C, your shrinkages will be compensated by what? Riser. From C to D, it will be compensated by providing shrinkage allowance or pattern making allowance. And here three temperatures are shown which you have to look carefully. TP is your pouring temperature, TF is your freezing temperature, and TA is your ambient temperature. And now let's look into some of these notes that are provided in the screen. First of all, we have a solid shrinkage allowance, other name, which is pattern making allowance. So remember this. Then solid shrinkage allowance are always expressed in mm per meter length. So for example, if you have this three lengths LBH, and it is given that you have solid shrinkage allowance. So solid shrinkages are given as this mm per meter length. So if you have solid shrinkage allowance given as 1%, then you will increase each of this length by 1% to get that solid shrinkage allowance value to just make this solid shrinkage allowance in the pattern, to just include that. So that 1% will not be multiplied with the whole volume, instead it will be multiplied with the individual sites, because that's how it works. Then we have the liquid and solidification shrinkages, which are expressed in percentage of shrinkage volume. So percentage of shrinkage volume means that it will be also always given with like for example 3% volumetric shrinkage is going to happen in this process A to C or AB and BC. Then you will be doing this 3%, the amount of shrinkage, the volume that has shrink, you will take it by multiplying that percentage with the total volume. Then you will get how much volume is shrink. So that is just the normal difference between these two types of allowances and two types of shrinkages, and how we are and just using them and how we are looking into them. Now the last thing that you have to note here is shrinkage allowance depends upon coefficient of thermal expansion, and which changes metal to metal, and dimensions L, and also it depends upon the temperatures TF and TA, because shrinkage allowance, when it is happening in CD, which is solid form of the metal, and which is having this first temperature as TF and final equilibrium temperature as TA. So this is what your shrinkage allowance is, alpha L TF minus TA. Now we have this question, what riser is designed to? So riser is designed to, the options are given and the correct answer will be, the riser is designed so that it freezes after the casting freezes. If it is freezing before the casting freezes, then what will happen? The riser cannot compensate the shrinkages that are happening during this whole solidification of casting. So we need riser that is there. That's main aim of the riser, is to compensate the contraction. So it should be having that liquid metal freeze after the casting has contracted, and it requires the molten metal. So to provide that, it needs to be freeze after the casting freezes. Next we have this other question where it is asked that the contraction allowance provided, contraction allowance, which is also you can say that it is shrinkage allowance, nothing new. The name shrinkage and contraction means similar thing. So they are provided on pattern and core boxes to compensate for following type of contraction. So for compensation of solid contraction, we are providing this allowance on the pattern, and also on cores. Again, core is used to make hollow structures or holes. We will look into cores again as we move forward. When there is no room temperature change, the total shrinkage allowance on a pattern is independent of, and we have looked into the shrinkage allowance, that is the allowance that is given, as I've told, after the material or after the casting or molten metal has become solid. So it will be independent of pouring temperature, because there only things that are going to matter for the shrinkage allowance are freezing temperature, component size, coefficient of thermal contraction or expansion, as you can say, and also room temperature. But here the room temperature is not going to change, so it is not shown here in the options. So the correct answer will be A. While cubing of a while cooling of a cubical casting of side 40 mm, it undergoes 3%, 4%, and 5% of volume shrinkage. During this different states, liquid, phase transition, and solid. Volume of metal compensated from the riser is. So from the riser, only those volume will be compensated which are shrink or which has shrinked in the liquid and phase transition state. So those two volume will be 3% and 4%. So the correct answer will be 7%. The 5% volume, that is the volume that is shrinked during the solid state, will be compensated by the pattern making allowance or solid shrinkage allowance. Now the next question is having this casting size given to us. Casting size is 100 cross 50 cross 10, and all things are given in mm. Then we have this spherical cavity of diameter 4 mm inside this casting. Then we have pattern making allowance or shrinkage allowance as 3%. And as I have discussed before, 3% of what? 3% of this individual dimensions, individual sides. And we have to find the ratio of volume of pattern to volume of casting. And I have discussed this a lot of time. Whenever volume of pattern divided by volume of casting is asked and you are providing shrinkage allowance to the pattern, then always your volume of pattern will be greater than volume of casting, and you will find that volume of pattern to volume of casting will be coming out greater than 1. So let's look into what this question, how to do this question. And to do this question, you can do this very easily. Simple calculation is involved, but I don't want to just for you to just do this question and move on. I want to do you to do this question very quickly. So for that, I will have to draw a diagram and make you understand that how you can not waste time. So you have this casting of gray cast iron. This block is given and you have some dimensions. See, if you calculate the volume of this casting, you have to first calculate the volume of this block, which is very fine. It is not that hard. But then what you have to do, you have to calculate the spherical cavity which is inside this block, and this spherical cavity is having some diameter d, and this is your length into height into, so this is your height, this is your width, this is your length. So you will find that this calculation will take some time, because first you have to calculate the volume of the block, then you have to minus the internal cavity, then you have to repeat the same thing by now considering the allowance, that is the 3% given to the pattern. So it will obviously take time, and I think that is not the correct, and that is not the correct approach, because this question is not that, it does not need that much time, it is not that hard. So what you will do, you will write volume of pattern, then volume of casting, and you have to find these two ratios. So you will take volume of casting as V, and you will also take volume of pattern as V. Now this 3% will individually increase every length or every dimension. So it will increase and make this 100, 103, it will make this 50, 51.5, it will make this 10, 10.3. And how we obtained this final value, we have increased it by 3%. And how to increase this by 3%? We have multiplied this 100 with 1.03. We have multiplied this also with 1.03 to increase this with, or increase this by 3 percentage. So this 1.03 is multiplied 3 times because of the 3 dimensions we have to increase the size of, and we can say the final volume therefore can be increased by this 3 times only, or this 1.03 cube will give us the into V will give us the final volume of the pattern. And same you can do for this diameter, and then calculate that and minus that with the block volume, and therefore you will just cancel it and you will find this answer in very quick manner by doing this trick. So the correct answer is coming out as 1.09. So this is your correct answer, and we can calculate this very quickly without wasting time and without calculating the individual volumes of pattern and casting, by just taking it V and by just multiplying with the factor that is going to increase the volume of pattern. And we will look into one more question where this method can be used. So let's move forward. So here are some materials that you have to remember. First is brass, then we have aluminium, then steel, then grey cast iron. So in casting you have to remember these materials. Why you have to remember brass? Because for brass solid shrinkage is maximum. Since solid shrinkage for brass is maximum, it requires largest size of pattern. And then we have aluminium, which requires more volume of riser because of liquid and solidification shrinkages for aluminium being more. Then we have grey cast iron, and grey cast iron means that then we have steel. Grey cast iron has something other going on. Then we have steel, where total shrinkages, that is the shrinkages happening in solid, solidification and liquid states, are going to be maximum for steel. So it requires sufficient amount of riser also, and sufficient size of pattern also to compensate these shrinkages. And grey cast iron, it is a little bit different here in liquid and solidification state, that is the states before this grey cast iron liquid and form has become fully solid. Expansion is going to occur. Why expansion is going to occur? Because the conversion of carbon into graphite flakes is making the material expand when this temperature is decreased, and the material, the grey cast iron molten metal, is going from liquid to solid state. And when it has become solid after the phase change, you will get contraction as usual. Which of the following pattern requires the largest shrinkage allowance while making a pattern for casting? So the material which requires the largest shrinkage allowance is brass. Shrinkage allowance on pattern is provided to compensate shrinkage when, and the answer will be temperature of solid phase when drops from liquid to room temperature, then we need this shrinkage allowance. So this is the shrinkage is shown, that is the temperature change with the time, and you can see in CD we require shrinkage allowance. So this is the question where we have to find the side of the cube which is getting this shrinkages, volumetric shrinkages as 4% and 6% in solidification, solid, contraction respectively. And you will see that no riser is used, so your final size will be less than the size 50, because the contraction is going on and no allowances is given, no riser is given. So this will make the final casting due to this shrinkages less. So since volumetric contraction is given, so what will be the final size? It will be A is equal to cube root of 50 cube initial volume, then we have to multiply it with 0.96 first of all, that is the shrinkages that is happening in the solidification state or process, and then we have to multiply it with 0.94, and we will get the final answer as 50 cube into 0.96 into 0.94 cube root 48.317, so it will be 48.32 mm. Grey cast iron block of this size are cast in sand molds. And again, we are giving pattern making allowance 1%. Ratio of volume of pattern to that of casting is asked here, and we will do similarly volume of pattern divided by volume of casting. We will take volume of casting as V, volume of pattern as also V, but we have to multiply that to account for these pattern making allowances. So 1.01, three sides are there, so it will be cube, and this will be your final answer. You can do this in any other way that you desire, but doing this in this way, 1.03, I've just calculated it. So doing this question this way will obviously take less time and less calculation mistake, because you are just taking this 1.01 cube and making the answer, calculating the answer. And you can always say here that these two were the wrong answers, because since you are making this ratio of pattern volume to casting volume, and this ratio will be more than 1, because pattern making allowances will increase the pattern's volume or size. Now we have draft or taper allowances. So all the surface parallel to the direction in which pattern will be removed are tapered slightly inward to facilitate safe removal of the pattern. This is called draft allowances. And as you can see in the first figure, that if you are removing this, then there can be a chance of disturbing the cavity, and due to this, due to easy safe removal, we are just tilting it or tapering it a little bit, the patterns, and that allowances depends upon the vertical height or vertical length, which is h. And as you can see, x is the draft or taper allowances, and if theta, which is the draft or taper angle, we are taking it as half to 2 degrees. So this angle will be giving the value of x as h tan theta. So x will depend upon this theta, which is usually this half to 2 degrees, and it also depends upon h. If h is very large, then x will be large, therefore your draft or taper allowance is large. And if h is small, then x is very negligible and we can ignore that. So draft or taper allowance is optional. Why it is optional? It depends upon height of the pattern. And then we have a machining allowance. It takes care of the extra material that will be removed to obtain a better surface finish. And the most important thing, first look into the figure. Here we are providing extra material per surface, and this extra material will be removed due to machining to obtain the final casting. The casting surface finishes are not very good. Investment casting, it is having better surface finish, but sand casting and other casting mainly are not having that good surface finish. So machining allowance is, I think it is a must, because you have to provide this better surface finish once casting is made, and it is provided as per surface. So this is very important point, and you have to remember this thing, that how the machining allowance is given. Note, the amount of machining allowance depends upon size of silica grains, size of casting, material properties, material distortion, finishing accuracy, and machining method. Some of the things that I am showing here, you have to just read it 3-4 times and then move on. Don't take time and understand those things, because these are just objective type questions which can be asked from this little bit of notes, and no need to just go on very deep and waste your time here, because theory you should only study those things which are going to be asked, and try to cover as much as possible, but don't try to go in deep, or don't try to remember each and everything word by word. So in the theory part, so just read it once or twice, what are the amount of things this machining allowance depends on, and then move on. Now this silica grains which we are using to make this cavity, which we are packing around this pattern, are of two types: fine or coarse. The fine grains are facing sand, which is just near the cavity, near the your pattern, and then we have backing sand, which is to support. And obviously, as you can see, facing sand will give better surface finish. Calculate the dimensions of the pattern shown below by considering the machining allowance of 1 mm on each surface. 1 mm on each surface. And here you have to look into this, and here you can see that the exterior external surfaces, that is 100, 80 and 400, they are increased by 2 because 1 mm on each surface is provided as machining allowance. So 100 becomes 102, 80 becomes 82, 400 becomes 402. But internal, this diameter of the hole does not become 52, it becomes 48 because we are adding material and hence the diameter will be reduced by 2. So machining allowance, that is also written in the note at the bottom right corner of the screen. Machining allowance is a positive allowance, means metal is added for both internal and external surfaces. Shake or wrapping allowance, it is a negative allowance. Remember, the only negative allowance that we are studying in this class for GATE examination is this shake or wrapping allowance. So size of pattern is reduced. Draft allowance, as we have discussed, it is optional, it depends upon height, but shake allowance is compulsory. What is shake allowance? Around the pattern you have molding sand, and if you are shaking the pattern before removing it, then due to some adhesive nature of this due to adhesive nature of molding sand, some of it can get sticked, and if for example one unit of that sand gets sticked and forms a layer, so your final casting will be obtained as 102 size of the side length size. So this 102 will be not desired by us, so we have to take it into account this shaking or sticking of this mold sand, and we have to take the this allowances into consideration and reduce the size of the pattern to account for this shaking or wrapping, and hence this extra layer that is getting sticked with the pattern and getting removed and making the casting increase. So this pattern size is reduced to compensate for that. Negative allowance is provided on the pattern to take care of, and the answer will be, just we have studied it, D, shake allowance. Distortion in casting may occur due to so this is distortion or camber allowances that we are going to discuss right now. And as you can see, before going through this definition, let's look into the figures. So original casting, if it is L shape, but this casting after solidification may have this distortion, and hence we have to provide this camber so that even after distortion the original casting looks like the one that we desire. So this distortion in casting, how this is happening? This is happening due to internal stresses. And how these internal stresses are generated there or caused there? It is caused due to unequal cooling of different sections of the casting and hindered contraction. So unequal cooling, because this cooling will depend upon the length, and that length of different parts, as you can see, are different here. Some of the parts, for example, the distorted part here is having outer length different than the inner length of one side of the length is different than the other side of the length. So there will be different cooling there occurring, and due to which distortion will occur due to internal stresses. It is a zero allowances. You are just making the part shape change to account for this distortion, and amount of allowances depending upon the ratio length by thickness. Pattern materials. Pattern we have studied, it is used to make cavity, but what materials the pattern are made up of? Pattern can be made up of wood, metal, plastics, plaster, synthetic material, wax and mercury. So mercury and wax are used for complex shape objects when we have to create them. So wax is used when investment casting process is done, and for mercast process we use mercury. And mercury is having this special property that it is solid at minus 39 degrees Celsius. So it will be liquid at room temperature. So you don't have to give that much of pouring temperature to make it liquid. It will be just liquid at room temperature. So that is just a little bit of information about Marcas process and mercury there. And one thing that you have to note here, double shrinkages. So when metal pattern are cast from wooden master pattern, remember double shrinkages must be provided on the wooden master pattern. Why? Because now the shrinkages will happen for both metal pattern and casting. So therefore, wooden master pattern from which we are creating these different metal patterns will need that double shrinkages to account for both of this contraction in casting and metal pattern. Now types of pattern, let's quickly look into them. Solid or single piece pattern. Simplest type of pattern to produce simple shape and size objects. One surface of the pattern must be flat. Split piece pattern. Now in the split piece pattern, we are having this two pieces, and these two pieces are going to be assembled together with the help of dowel pins. So this dowel pins have this impressions over which it is going to be just kept, and hence this two split pieces can form one complete piece. So these are for complex shape and size pattern. So the splitting is happening along the parting line. To get required cavity, split pieces can be removed from cope and drag boxes separately. Loose piece pattern. For projections and undercuts, we use loose piece pattern. Here we have a tapered sections and simple projections. Then we use loose piece pattern. Complex projections, we use plastic pattern. We will look into plastic pattern when we encounter that in this class. But again, I am going through these types of pattern very quickly because till now I don't think that or one or two questions has come in match the following, but they are only asking this characteristic and specification of types of pattern. So I have provided that in the slide. I will not go through the whole discussion in this class in detail because that is not needed. So we will just look into what their characteristic are, what their uses are, and how they look like, so that you can get an idea of this types of pattern and have this complete information for GATE examination. Gated pattern. So gated pattern is used to produce simple patterns in mass production. So you have four patterns in the figure shown, pattern 1, 2, 3, 4, and all these patterns are joined with the single gate, and therefore in this gated pattern many patterns are joined through this gating system, so we don't require individual gating system. So time and cost of making them separately are just saved here. Match plate pattern, it is used to produce complex shape just like your just like your gated pattern, it is also used for mass production, but here simple patterns, here complex shape for match plate pattern. And match plate, you can see where it is just between these two pieces, and runner and gate are integral part here of the match plate pattern. Then we have a sweep pattern which is used to produce complex shape of objects in mass production. So again mass production and for complex shape, but only axisymmetric objects can be made here. Here we have a triangular 2D object and we are sweeping it, revolving it around an axis, and we are forming a cone. So this 3D object, 3D cavity is created from this 2D object or 2D pattern, and examples are cones, bells, which can also be of large size, cylinders, etc. All these examples are axisymmetric because that is what this sweep pattern can make. Follow board pattern, the last type of pattern, and here you can see follow board, which is usually made up of wood, and as you can see in the figure, you can guess what it is needed for. So it is needed to just support this structurally weak members. So provided to support structurally weak members of the pattern because of possibility of ramming force. So ramming force we have to do, for example, hand ramming. So some force will be applied to tightly pack the sand so that dimensional stability is achieved by uniform ramming, and while doing that the pattern which is having weak structure can get broken, and therefore we need this follow board to avoid that. So follow board pattern, which is usually made up of wood, functions this thing. So that is what we have studied as our first part of the, or my first slide of the casting. Now let's go into my second slide. So let me just open the second slide, and I hope you are having a good time here, having understanding the things that I am teaching in the class. So let's move forward and discuss the. So let me first of all, yes, adjust the camera. So let me open the second slide here. So I have the second slide with me, and we will start it. But before that, let me just prepare for that slide by drinking water. So let's start the other thing here in casting. So now let's talk about core design and core. So what are cores? I have already talked about them in this class. They are used to make holes, openings, recesses, etc. in castings. And in the figure you can see first of all a cavity inside which you are seeing core, and around which you have molten metal. Molding sand is also seen around this whole cavity, and core prints are seen also chaplet. So this all the terms we will discuss in this core and chaplet discussion. So first again, cores are used to make holes and opening recesses etc. in castings. Core prints are projections on the pattern made to support the core inside the mold cavity. If there are no core prints, then the core would get displaced. So core prints, so that provided to not so that cores does not get displaced. Chaplets are metallic objects used to support a core and are placed between a core and the mold wall. So the function of chaplet again to support the core, and since they are provided between this core and mold wall, and they are just surrounded by this molten metal, so chaplets are going to be made of same material just as your molten metal or just as your final casting, because they are going to be melted at the end of the process. If they are not melting completely, then it would create the weakest section there, and a mold wall leak can occur. So therefore they need to be melted, and they are now part of the final casting after this whole process. So they are of the same material just like castings. Core design, so we have this again, you can see the figure, and in the figure you can see that the core is having this net buoyancy force acting in the upward direction trying to displace it, and this recesses is preventing it. So that net buoyancy force that leads to shaking of the core is given by weight of the liquid metal displaced by minus weight of the core. So weight will be rho gv. Rho is the density, g is the acceleration due to gravity, v is the volume of the core. that has displaced the molten metal. So rho m in the formula that is seen in the screen right here is density of liquid metal, and rho c is density of core material, and v is the volume of the core which has displaced the molten metal inside the cavity. So to calculate this net buoyancy force, what you can do is you can take the difference between this liquid metal and core material density and multiplied them by them with this G and V. And core are made up of the molding sand plus some of the binders are there, some of the additives we are adding in that, and liquid metal is again having will have obviously more density than this core material, which is just sand plus some modifications. So obviously the density difference will lead to buoyancy forces acting in the upward direction and core getting displaced if there is no recess or if no support is provided there to counter that. So core sand is molding sand plus some organic binders and linseed oil, molasses, etc. And dielectric baker is used for core making. So this was asked in one of your gate examination, I think in PI. So you have to remember that dielectric baker is a machine which is used to make cores. So remember this information. And now we have this formula which is very important because one of the gate questions has already not gate, yes, I think one of the gate question was asked using this formula. So you have this P which is net buoyancy force, and you have this P less than or equal to 3.5 AC. Why? Because if this P gets more than this value, then this recesses will not be able to support the core and the core will get displaced. And here remember that AC will always be in centimeter square, which is core print area, and 3.5 is in Newton per centimeter square. That's why AC should always be in centimeter square to get the P in Newton. So we have this question here that is given. It is given in the question that we have sand casting of a hollow part of lead, cylindrical core of diameter, height is given, and densities of the core material and lead are also given, and net buoyancy force that is trying to lift the core is asked. So what we will do, we will simply do the density of lead minus density of this core and into G into V. So this will give us the answer. So what answer we will be having here? So we have to find the net buoyancy force, and I think something has been done wrong in the calculation. So let me look into it once again. So yes, it is coming out as C, which will be the answer. Bentonite is commonly used bonding material for dry sand cores. So as I have told you before, the molding sand will have some of the binding materials uh, which are going to be added to the molding sand to make it proper for this casting process, and bentonite is one of them. So this is true. Constituents of molding sand. Molding sand is having 70 to 85 percentage silica sand. What is silica sand? Silica sand is nothing but beach sand, which is most commonly, most abundantly available here. And you can find that it is 70 to 85% in your molding sand that you use in casting processes. Clay is next with 10 to 20 percentage. What is the function of clay? Clay is used as binding material, that is to bind this sand properly so that a proper mold cavity is formed. Then we have water or moisture, 2 to 8 percentage. This is to activate the binding properties of clay powder. Additives are there, 1 to 6 percentage for enhancing properties. Properties of molding sand, we will quickly go through them. First, we have refractoriness, which is ability of the molding sand to withstand high temperatures without breaking down or fusing. Permeability, ability of molding sand to allow easy escape of gases. Flowability, ability of molding sand to flow uniformly to all corners of the mold box when rammed. Strength, required to retain the shape and size of the cavity. Hardness, required to minimize erosion and withstand the molten metal pressure. Adhesiveness, bond formation between two different materials. Cohesiveness, bond formation between similar materials. Collapsibility, ability of the molding sand to allow free contraction of the metal. This avoids the tearing, hot tearing or cracking of the contracting metal. And this collapsibility will be must for cores, because it will contract when there is core and your metal is contracting, and if it is not, the core material is not, if not having this collapsibility, then it can produce hot tears or cracks in the material or in the metal that is contracting above it, so that obviously we don't require. And here another thing that you have to notice is flowability is the property of molding sand, and we will encounter one another property in casting topic. Flowability is this molding sand's property. Then there is fluidity that we will discuss. That property is molten metals property. So just remember these names and don't get confused there. Which of the following is not a property of the molding sand? So as I have told you, fluidity is the property of the molten metal, not molding sand. For molding sand, the property which is starting from F is flowability, which is nothing but the ability of the molding sand to flow uniformly to all corners of the mold box when rammed. Permeability will decrease. So some notes I am just going through. Permeability will decrease if clay powder increases and fills the void. So permeability, it is important to get for the gases to escape, and it will decrease if clay powder which is there to do the binding increases and fills the void. Hence there are no way or no voids for the, or less voids for the gases to escape, so permeability will decrease. And also more permeability is equal to less hardness, or less hardness or more hardness will be there when there is less permeability. The second point, so second point is also very important, and you have to remember it, that if hardness is going up, your permeability will go down. Mole hardness number is usually between 0 to 100, and or it is between 0 to 100, we are taking it in this scale, and average is usually between this 60 to 80. If hardness is greater than 80, then there will be less permeability, so gas defects will be there. But if hardness decreases below 60, then dimensional stability will decrease. And how this dimensional stability can be achieved is by uniform ramming. So your hardness should be between this to not have this gas defects, and to also not have this less dimensional stability. Molding sand should have sufficient thermal conductivity and low coefficient of thermal expansion. Strength and hardness, if they are increasing, collapsibility and permeability will decrease. So this again is very important, the second to last point, that whenever in the question you are having strength and hardness going up, then your collapsibility and permeability will go down. Green sand, whenever you are encountering this, remember that green sand is molding sand which contains moisture. So the green sand term is accounting for this moisture, or this representing this moisture. Hardness of green sand mold increases with. So hardness is going to increase when permeability is going to decrease. So C is the correct option. Don't get confused with the green word here. Green sand represent the moisture, but here there is no use of moisture because we are talking about hardness. Green sand mold indicates that mold contains moisture. D will be the correct answer here, as we have discussed. Now we have the permeability and percentage of water variation. So above 8% water will fill voids and not allow gases to escape, hence permeability will decrease. So permeability will first go up, reach a maximum point at this 8% of water, then it will go down. So you can say permeability is going through a maxima. Now we have flow ability, which is the ability of the molding sand to reach all corners of the mold box, and with percentage of water, it is following the just the opposite approach of this permeability. It is passing through a minima. So first it is decreasing to uh, getting this least value in the 6% of water, then it is getting increased. And as you can just say it by logic also, that if the water is going to be added in more percentage, you are going to see the molding sand is behaving more and more like a fluid, so its flowability will increase. So that's why it is increasing after this 6%. Increase in water content in molding sand causes flowability to go through a maxima. No, it was going through a minima. We have just studied that. Permeability to go through a maxima. So B is the correct option. But remember, in your GATE examination, never select an answer without reading all option, because some other option can be there which might be also correct and which might also be more correct than the one you have read before. Compressive strength to go through a maxima. So that I think we don't have studied yet. So just that will be not there. And strength to go through a maxima. So correct answer will be B. Permeability is determined by measuring the rate of flow of air through the AFS standard ramped specimen under a standard pressure. And what we are talking about now is permeability number, which is given by the equation VH by PAT, where V is volume of air passing through this sand specimen, which is AFS standard ramped specimen, and this standard specimen is having height 5.08 centimeter, that is 2 inches, and its height is equal to diameter. The pressure of air is given in gram per centimeter square to calculate this permeability number. Cross sectional area of the specimen is A, and time taken by the air to pass through specimen in minutes is also there in the formula. So this formula is not dimensionless, so just remember this point. You don't have to remember the dimension, just remember the formula. So you can know the dimension by yourself. And generally this permeability number is between 60 to 120, so that you allow proper gases to escape also, and also have the proper dimensional stability. So 60 to 120 is the permeability number that should be having by this generally accepted. And if permeability number is more, for example if it is 120, then what will happen, we can say that time taken by this the air to flow through this specimen is less, so permeability is more. So permeability number, again I am reading the definition, it is determined by measuring the rate of flow of air through the AFS standard ramped specimen under a standard pressure, and that pressure is given in gram per centimeter square. And for this permeability number calculation, you have to remember this value, because it might happen that this is not given in the question, so you have to remember them. And again, this is AFS standard, American Foundry Society standard. So just remember that this why this H and D are like that, because it is taken as a standard. by the AFS. Permeability of molding sand was determined using a standard AFS sample by passing 2000 cc of air at a gauge pressure of 10 gram per centimeter square. Time taken for the air to escape was 1 minute, and we have to find the permeability number here. So permeability number, as we have just discussed, it can be easily calculated by VH divided by P A T. So VH divided by P, area will be pi by 4 D square, then we have T. So T is 1 minute and T is to be put in minute, so that is also important. Don't convert it into seconds. And now this answer will be, so it is coming out as 50.1275. So 50.12 is the permeability number, which is D. And we can look into that here, that permeability number is coming below 60, so it is not going to be acceptable, or generally not what we expect permeability number to come. So it represents that permeability will be less, and therefore gas defects may occur. Now let's talk about additives that molding sand has to make them more proper for this casting process. Sawdust or wood flour, they are used to increase collapsibility of both mold and core, and it also increases permeability. Linseed oil, molasses, dextrine, etc. These are organic resin binder, and they increase the dry strength and hardness of the mold. Coal dust for producing or reducing atmosphere during casting, therefore no oxidation of the metal, and hence a better surface finish. And here you can easily remember this, that the first additive is sawdust or wood flour that we have studied here, and they both are increasing collapsibility and permeability. And whenever this properties go hand in hand, and what are the, if these properties are increasing, what will decrease? Strength and hardness. So those two are now increasing, are getting increased by the other additives here, which are linseed oil, molasses, dextrine, that are organic resin binders. And coal dust for reducing atmosphere, because coal carbon is going to do that, and therefore no oxidation of metal, and hence better surface finish. Woof floor, which should be wood floor. So wood floor, just we have studied that, is added to core sand to improve collapsibility of the core or permeability also. Now gating design, we have to study this, and this is the gating system. So this system, as you can see, it is having this cavity, primary cavity and secondary cavity, and the primary cavity is just said here as cavity, which is in the shape, or which is the replica, not the replica, which is in the shape of the casting that we have to obtain. The first thing that we will encounter when we pour liquid metal is the pouring basin, and that pouring basin will smoothly let the molten metal flow to the sprue after passing through strainer, which will just clean it off, and then it reaches the sprue base wall, where it will encounter splash core, which will make its flow smoother and make its transition or entry into runner smoother. And then after passing through runner, or after passing through runner, it will enter the skim bob, which will just clear off the light and heavy impurities, both of them. Then through this gate section, it will pass and enter the cavity finally. And then we have riser, which is there to compensate for the shrinkages that is happening in the liquid and solidification states. And also riser's job is to allow gases to escape, and that gases that are generated in the casting process. So we will look into them in details. So let's start the discussion. So first of all, good gating design. So a good gating design is one which is having proper distribution of molten metal without air aspiration effect. What is air aspiration effect? We will also look into it as we move forward, but just to introduce it, air aspiration effect is absorption of air with the liquid metal stream, hence porous casting structure is obtained. So that will be avoided, that should be avoided if gating design is to be said as good. Then we have no mold erosion. Molding erosion should not be taking place so that it can not alter our casting or primary or secondary cavity. No splashing without turbulence. So if there is no turbulence, there will be automatically no splashing. So they go in hand in hand. No excessive temperature loss, as the molten metal has to fill the whole cavity properly, not solidify before that. No gas entrapping without slacks, and maximum casting yield. What is casting yield? It is casting volume divided by the total volume, that is casting volume plus gate volume. Note liquid metal, laminar flow, avoid oxide formation. Oxides for non-ferrous metal, high density, hard and brittle. Oxide for ferrous metal, lower density, turbulent flow and high velocity. Okay. So what is written here, that oxides for non-ferrous metal are difficult to deal with because of their high density, hard and brittle nature, but oxide for ferrous metal are having lower density. So oxides which are forming due to this turbulent flow will be okay for ferrous metal. They will not create that much problem. So for ferrous metals, turbulent flow and high velocity are okay, but for non-ferrous metal they are not okay. We have to keep the flow laminar. Excess turbulence have other benefits also apart from this oxide formation: inclusion of slag, air aspiration effect, erosion of mold walls. Proper gating system in metal casting, and it should first of all influences the freezing range of the melt. No. Compensate for the loss of fluidity of the metal. Yes. Facilitates top fading of the metal. No. And avoid misrun. Yes. So it will be QS. The part of the gating system which regulates the rate of pouring of the molten metal is called choke, because it is the smallest area, and this area is the first that we calculate. And it what its importance are, we will look when we study unpressurized and pressurized gating system. But for here, remember the part of the gating system which regulates, which means which controls the rate of pouring of molten metal, is choke or choke area. Primary purpose of sprue in casting mold is to feed molten metal from pouring basin to the gate. So it should be C. Primary function of riser is to feed molten metal to casting as it solidifies. So A will be the correct answer. Riser is also having this secondary function of allowing gases to escape, but that is not the primary way of gases letting escape, or also that is not the primary function of riser. So the primary function will be to feed the molten metal as the casting solidifies. So that is to avoid that liquid solidification shrinkages. During filling process of a given sand mold cavity by molten metal through a horizontal runner or cross section circular, the frictional head loss of the molten metal in the runner will increase with. So frictional head loss will be given by F friction factor L V square divided by 2GD. So increase in runner diameter will make this friction head loss decrease. Decrease in internal surface roughness, since the surface roughness is getting decreased, so it will make the frictional head loss also decrease, because the smooth flow will not allow losses to happen when as compared to the this surface roughness, if it is very much there. Decrease in length of the runner. So if length of the runner is decreased, we can see from this formula that of the head loss, that your frictional head loss will also decrease. If increase in velocity is done, then the frictional head loss will increase. So the correct answer will be D, as HF is proportional to V square. Good design for a pouring basin. Here you have to remember some of the parameters or some of the standard dimensions. If D is the top sprue diameter, or diameter of the topmost part of sprue area, then the height of the pouring basin will be 2.5 D, and this curvature that you can see in the pouring basin is 25 R. Pouring basin is said to be good when it reduces the velocity of the liquid metal in the sprue, and hence it reduces the erosion. So pouring basin, what it does, reduces velocity of the liquid metal in the sprue to minimize erosion. Now we have this sprue, and 1 2 is the height of 1 2 is HC, which is pouring basin height. Then we have 2 3 point, the sprue, which is having a tapered section. Why, we will look into it. And the sprue height is HS. Total height is HT. V3 here will be very greater than V2. As you can see, the area of V3 or area at 3 is less, and if volumetric flow rate is constant, which is Q is equal to AV, if area is less, V will be more. So that you can see. And velocity at any point is given by under root 2gh. So Alt plus F4 is going to close this thing. So this is a very I think old trolling method. So I think you should try better if you want to do that. So King 003, very lukewarm trolling. So try to do it better if you want to do this type of things. Anyways, design of sprue. The velocity is given by under root 2gh, which is nothing but came from Bernoulli's equation. And you can see velocity at 3 will be calculated by under root 2ght, that is height above the 3 point is ht, and therefore that is the formula that we are going to use to calculate the velocity at 3. And velocity at 3 will be greater than velocity at 2. And why? Because of the area there being less. Now let's move forward. So we have this equation that we are getting at the final step, that is ht by hc is equal to a2 by a3 whole square, and this is in the form of parabola, that is y is equal to x square is parabola. So this is similar in that regard. So you can say that the ideal shape of sprue, that is between the point 2 and 3, is a parabola, and we will look into that. But before looking into that, you can see how that ideal shape has come. It has come by equating that using this continuity equation or volumetric flow rate equation, and again using this velocity equation, that is under root 2gh. So just remember, don't remember that ht by hc is equal to a2 by a3 whole square. Just remember that ideal shape of the sprue will be parabolic. So this is ideal shape of sprue, and actual shape, that is tapered, is different, because manufacturing difficulty does not allow us to make this ideal shape, or does not allow, we should not say, we should say that it is difficult to make them. And this actual shape, which is tapered, is fulfilling the same purposes. So we don't require that extra difficulty and making this ideal shape. So just remember that ideal shape parabola, actual shape tapered cylinder. So air aspiration effect, let's discuss that. So free falling liquid metal is going to look like this. So you can see this shape of free falling liquid metal, that is the first figure, is tapered, or just looking like a tapered cylinder. And if we are using a normal cylinder which is having this top area and bottom area same, that is the normal cylinder, you will find that there are low pressure areas going to be obtained there, and hence air aspiration effect will occur. What is air aspiration effect? We will look into that, but here just look into why air aspiration effect and when air aspiration effect will occur. And if we are using tapered sprue, then you will find that there will be no air aspiration effect because it matches the free falling liquid shape. So air aspiration effect is entering of gases from baking of organic compounds present in the mold into the liquid metal stream. Or you can say air aspiration effect is just sucking of this air that is generated during this casting process and getting this liquid metal stream mixed with this air. So this produce porous casting, and pressure anywhere in the liquid stream should not be negative. This is done to avoid the air aspiration effect. And to avoid air aspiration effect, the best thing that we can do is to use a tapered cylinder or a parabolic cylinder, this sprue. So runners are of two shape that we have you can see here, and the first shape is trapezoidal cross section. It is to minimize turbulent losses, but the surface area here will be more, and therefore more heat transfer losses will be there in this first type of runner. For second type of runner, there will be turbulent losses, but you can minimize the heat transfer because surface area is less, and surface area if is less for same volume, then there will be less surface for the heat transfer to occur, and hence your surface area will be if less, will lead to minimization of heat transfer. Gate or in-gate, actual entry point through which liquid metal enters the mold cavity, as we have discussed when we were looking into the gating system figure. Gating design is classified mainly into two or modified three types: top or vertical gating system, bottom gating design, and parting line gating design. So let's look into them. Top gating design. So this top gating design, you can see you are pouring metal from the to the, first of all, pouring basin, then it is passing through sprue, then directly it is filling the mold cavity from the top. So this is the formula that you have to remember. TF is equal to volume metal is achieved due to fast filling. Bottom gating design, velocity of the liquid metal in the cavity is negligible, and as you can see the velocity is negligible. It is filling from the bottom part after passing through this runner. So the metal will start from filling from the bottom and it will go all the way to the top. So that's why bottom gating design. No turbulence or splashing of the liquid metal because of the lower velocity. And it can be used for ferrous and non-ferrous metal. Unfavorable temperature gradient of the liquid metal, therefore non-uniform properties. And in the previous one we studied, that is top gating design, we had this properties uniformly because of the favorable temperature gradient. So again, the derivation you can do by taking V3 is equal to under root 2g ht minus h, and again the amount of liquid that is at 3 and at the mold cavity region, inside that just equate them, integrate them, and you will find the filling time as 2 am bracket under root ht minus bracket under root ht minus hm, and dividing this whole thing by area of gate multiplied by under root 2g. So the thing that you will notice here is in the filling time formula for top gating system you have under root 2g ht, but here only under root 2g. The second thing is here there is 2, here there is no 2, so don't forget this 2 that is there in the formula, because if you forgot that, you can easily make the calculation wrong. So that is one of the common mistakes or common error that you do if you are not revising the formula for properly. So just remember 2 is there in the bottom gating design formula for filling time. So there is a note, if hm is equal to ht, that is if the height of the mold is equal to this total height of pouring basin plus sprue, then you will find that the time required for filling in the bottom gating system is twice that of top gating system. And how it is happening, just put in place of HMHT and see for yourself. I have done the calculation or derivation here. So just the bottom part, you have to remember that TF bottom is equal to 2 TF top if HM is equal to HT. Parting line gating design. So this gating design is getting the advantage of both top and bottom gating designs. It is most commonly used gating design since it is getting the advantages of both. And top gate and bottom gate are, so A is your, so I should write here B, here A. So here you can make this easy mistake. Somehow I've written that wrongly. I just noted that this in one of my classes, but I just forgot to do the correction here. So don't think that the A is at the top, so it should be top gating system, and is at the bottom, should be bottom gating system. That is now not how the top and bottom gating system are just uh, represented or just defined. Top gating system is when your molten metal is entering the mold cavity from the top, it is filling the mold cavity from the top, and when your filling starts here, the molten metal will go from the this runner to the part B from the top. So that will be your top gating, and B will be therefore your top gating. And A, when the B is filled, your A will be behaving like the bottom gate, because your molten metal will now come from the bottom and start filling this region A. So A bottom gate, B top gate. And the line which is dividing these two gates are parting line, is parting line. So we have another gating design, step gating design. Simple thing that we have to just remember here, that is to fill very large size mold without causing turbulence and splashing of the liquid metal. We are using this step gating design. So here we have divided this mold box into three A, B, C, and these three gates are there through which it is entering. Why it is entering? To fill very large size mold without causing turbulence and splashing of the liquid metal. So now we will do some questions after a little bit of a break there. I think 1 minute or so will be, 1 or 2 minutes will be fine. So let me just take a break here and do the question. We will take a lengthy break of 5 or 10 minutes after we have completed the casting, but right now I think 1 or 2 minutes break just to get my voice back to normal will be fine. So that was a quick little break that we took. So let's resume the class. So what we were discussing is the gating designs, and I hope you have this gating design clear. So, so this is the question that we have to do. Some of the questions, let's look, which are required to do this revision. What is the velocity of the steel at the bottom of the sprue if the sprue is 30 centimeter height, and having this 30 centimeter height, and this frictional and other losses are 20 percentage? So simply the velocity will be given by under root of 2g h s, because there is only sprue height is given, and then we will take this 0.8, which will just account the 20% of loss. So our answer will come out as, let's see here. So it will be 2.17 meter per second. The optimum pouring time for a casting depends on several factors. One important factor among them is, so optimum pouring time, location of riser, porosity of the sand mold, fluidity of casting metal, area of pouring basin. So since here pouring time is asked, optimum pouring time, then we have to here write fluidity of casting metal, because that will depend how much we have to give time to pour the liquid metal. Height of the down sprue is 175 mm and its cross-sectional area at the base is 200 mm square. The cross-sectional area of the horizontal runner is also 200 mm square. Assuming no losses, indicate the correct choice for the time in seconds to fill the mold cavity of volume 10 to the power 6 mm cube. And you have to use this 10 meter per second square acceleration due to gravity. So simply we will use the filling time formula, which is TF is equal to volume of mold divided by area of gate under root of 2g ht. So here we have been provided with height of sprue, and we have been provided with the cross sectional area of runner and area at the base. So there is no way to provide this height of pouring basin, because height, total height ht here should be hs plus h pouring basin, but here we have to take it 0, because in the question there is no means given where by which we can calculate that. So the correct answer will be simply putting this values and getting the correct answer, and I think you can do that by your own, since you have to only put the value, and I have also done this at the or in the previous classes. A mold has down sprue whose length is 20 centimeter. The cross-sectional area at the base of down sprue is 1 centimeter square. The down sprue feeds a horizontal runner leading into cavity of volume 1000 centimeter cube. Filling time is asked, same formula, same process. Find the answer, 2 marks, very easy question. Now we have a 200 mm long sprue, and it is having area of cross section at the top. So at the top it is having 650 mm square area. So we are also given with this molten metal flow rate Q, and we have to consider that the end of the down sprue is open to atmosphere, and acceleration due to gravity is 10 to the power 4 mm per second square. Area of the down sprue in the mm square at its end is asked. So here we have Q given to us, and if you take this, and this is one of the screens where figure is given. So if you take this 1, this 2 and this 3, then what you have to find, you have to find, since q is same, so you have to find a3, and for that you need v3. And you have this q, you have this a2 and v2. Is it given to you in the question? No. So v3, since you have this, don't calculate. v3 is not here equal to under root 2g hs. This is wrong. This is not your v3. v3 is equal to under root of 2g ht, where t is the total height above the point 3, that is the sprue height plus the pouring basin height. So just calculate this ht. And how to calculate ht? You have to first calculate v2, then by v2 you will get this height, and this height plus this 200 will give you this total height. Then just calculate v3 and get the final area. So again, I will not going to do this numerical part of the question, the calculation, not numerical part, because it will just take time and we have to cover a lot today. So let's move forward. In sand casting process, a sprue of 10 mm base diameter and 250 mm height leads to a runner which fills a cubical mold cavity of 100 mm size. So the volume of flow rate is asked, and to do that, what we need here is we have this volume of cubical mold. We can calculate that because size is given, and we have sprue base diameter, so area can be calculated, and we also have this height of the sprue, and there is no means to calculate the pouring basin height, so we can calculate the velocity there by just doing under root 2g height of sprue. So through that we can calculate the volumetric flow rate, that is velocity into the area at the base of sprue. All the data are given. Then mold filling time. So mold filling time, to do that, what we need to do is simply divide the volume of the mold by volumetric flow rate that we have obtained in the first part of the question. So I hope you will do this question and get the answer. Again, nothing new that we have to do here. All the things we have discussed before is coming into play here, so you can do this very easily. So a mold having these dimensions is filled with molten metal through a gate with height h and cross-sectional area a and mold filling time t1. Height is now quadrupled and cross-sectional area is halved. The corresponding filling time is t2. The ratio t2 is divided by t1 is, so t is your filling time, volume of mold, divided by the ag, area of gate, under root 2g h t. So let's say this height h is here and area is here, and mold filling time is t1. So let's just take t1 proportional to 1 by a under root h, and t2 it is given, it will be proportional to, height is now quadrupled, so 1 by 4h, and area is halved. So you will find it will become similar to t1. So t1 is to t2 or t2 is to t1. That you have to always do the proper ratio. Don't take t1 by t2. t2 by t1 is given, so it should be 1. Here both of them will be equal, but still make a habit of just doing the right thing. And here we have a final question from this topic, top gate, bottom gate, and that is parting line gate, and we have both top and bottom gate. So again, this is a conventional question, and this I think I will not do because it can easily take a lot of time. I have done in one of my previous classes, which you are free to check out, but I will fully tell you how to do this question. So you have a mold cavity, dimensions are given, and also here you are given a height, and filling time is given as 10 seconds. So just this two parts will be, this will be A this will be B. B will be taken, or to find the filling time in the region B, you will have to consider the region B that is below this parting line. So this is the parting line. So below this parting line, the region that is there is B. This is top gating, because the filling will be done by when the liquid metal enters into this region from the top, and A is bottom gate. So write down the formulas of that. TF 10 second is equal to filling time of B top gate and filling time of A bottom gate. Just add them both and get this final value of area AG. So I think again, not that hard, just the concept was there, which you have to take top, which you have to take bottom. Just put the formula and get the answer. Now fluidity, what is fluidity? I have talked about it before, that one of the properties we learned in casting, which was also starting from F name, was flowability, but it was for the molding sand. So now we have fluidity, which is the ability of the liquid metal or molten metal to flow into the cavity. Spiral test, which is used to determine fluidity. How it is used? Distance covered by the liquid metal in a standard spiral before solidification is the value of fluidity. So simple as that. And here are some properties and how they are affecting fluidity. So pouring temperature, if it is increasing, fluidity will go up. Viscosity will go up, so fluidity will go down. Density, if increases, fluidity will decrease. Percentage of water, if increases, fluidity will decrease, because if percentage of water increases, now the temperature of molten metal will give heat to vaporize or evaporate that water, and hence it will lose its heat content, and so it will solidify faster, hence losing fluidity, or fluidity will decrease due to increase in percentage of water. I hope that thing is clear. Surface finish of cavity, if is increasing, this fluidity will also increase, because there will be no losses due to the roughness being now less. So that also completes our another session or another part of this discussion of casting. Let me just open up the another part and complete this casting discussion. So I hope the slide is visible to you. So we will do this choke discussion, and also pressurized, unpressurized gating system. We will discuss that. Then what we will do is we will do the discussion of riser design, and then our casting discussion will be completed. We will not do the casting types discussion and casting defect discussion, because I have already done that in one of my classes, and doing that here, it's not feeling right, because of the other topics also which we have to discuss in forming and welding. And that reason due to that reason, we will only do this choke, pressurized, unpressurized, and riser design discussions. Again, all the things are available in this session of in our previous sessions, that is there in the playlist that you can find in the channel. So let's move, and you can also request some of these classes, because again, watching live classes, if you have to watch live classes, you can watch them from the archived or recorded ones. So it is better to come to a class and attend it live, and if you want to do that, you can always ask that in here when I'm taking a class or by contacting me. So let's discuss about this choke. So choke area is the minimum cross-sectional area in all the gating elements. We have discussed this as one of the question was asking which was the gating system part, which was regulating the molten metal flow or controlling. So choke area controls the flow of the liquid metal which enters the cavity. First parameter to be calculated in all the gating elements is choke area. The formula of choke area is M mass divided by rho density, TF filling time, CD correction factor, and under root 2G HT. So part of the gating system which regulates the rate of pouring of the molten metal, as we have already discussed this is choke. Choke can be placed near the sprue well to slow down and smooth out the flow, or choke is placed on the gates to make the removal of the part easier but induces extreme turbulence. So if it is there near the gates, removal of the parts is easier, but this turbulence is generated due to increase in the velocity of the molten metal due to this arrangement. So in a gating design, we have this gating ratio. What is the gating ratio? Gating ratio is the ratio of sprue area, runner area and gate area in this order only. So this is given as 4:2:1. It is used to produce casting of mass 20 kg, density is 2600 kg per meter cube, filling time is given as 10.4 seconds, and height of the liquid metal above the gate is given as 180 mm, and CD is given 0.96. We have to calculate dimensions of the sprue. Since gating design is given as 4:2:1, so this 1 means that the area that is here is less or least, and that is gate area. So gate area that will be equal to choke area, and choke area is given by the formula M divided by rho TF CD under root 2G HT. So it is given by this formula M by rho TF CD under root 2G HT. And we have been provided with this M, density, filling time, CD, HT, that is height of the liquid metal above the gate, and we just have to calculate CA. And after calculating this CA, to calculate this or to find this area of sprue, what we will have to do, we will have to multiply 4 into choke area, because if area of gate is 1, the choke area will be 4 times of that, and then we can equate it by pi by 4 into ds square to get this ds, that is diameter of the sprue. So I hope this is now understood by you and you can easily calculate it. In gating system, the ratio 1:2:4 represents always there in the same order. So it represents sprue base area, runner area, then in gate area. So the correct answer here will be A. Unpressurized gating system. So we have this unpressurized gating system when choke area is equal to the area of the sprue base. So choke area is at the bottom of the sprue. Velocity of the liquid metal entering into the cavity will be less. No turbulence and splashing due to velocity being less. Used for non-ferrous metal, again due to velocity being less, and no oxide formation because of again low velocity. Possibility of air aspiration is there. So this is one of the disadvantages here, and also the other disadvantage or limitation is that casting yield is less. So as you can see here in the slide, air aspiration is ticked mark, that is it is there, and casting yield is decreased, it will be less. So volume of casting will be not that much in percentage of the total volume, so that we don't desire. So if the gating ratio is given as 1:2:1, oh sorry, 1:2:2, that is smallest area here is clearly 1, and also 1:2:4, again smallest area is 1, which is sprue area, and that type of gating design will be known as unpressurized gating design. Pressurized gating design, choke area is equal to the gate area as here shown in the figure. So if gating ratio is having the last term as the smallest, then we can say the gate area is the smallest and hence it is the choke area. So choke area is at the gate, velocity of the liquid metal entering into the cavity will be high, so turbulence and splashing. Good for ferrous casting, but for non-ferrous casting you cannot use that for due to the oxide formation, and not good for light alloys also. This pressurized gating system, no air aspiration effect due to back pressure, so air aspiration effect will not be there due to back pressure here, and casting yield will be more. As you can see, one more thing in the slide that is very important, 1 is to 2 is to 1. If this type of gating system is given to you, then here AS and AG both are having this same and both are having this least uh, areas. So in that regard, you will always take the gating design as pressurized gating design, that is always take the area of gate as the choke area if this type of things happen. But if this is not happening, then you can take the just the what we have learned in the basics of this pressurized and unpressurized gating design. So the pressure at the in gate will be maximum with the gating design. So pressure will be maximum when it is pressurized gating design, and A and D are that pressurized gating design, but A is a more better one because here clearly the area of gate is smaller, not equal. But still D is also pressurized gating design, but here it is not asked about pressurized gating design, but it is asked where the pressure in the at the in gate will be maximum in the gating design given in the options. Now solidification time calculation, we have this Choverinov's principle, that is solidification time is proportional to volume by area whole square. So this will be solidification time will be equal to K V by A whole square. Solidification factor is the K, which is going to depend upon some things that we will discuss in the upcoming slide. But here remember this very important note, that V represents the amount of heat available and A represents the heat transfer. So for same amount of V, if A is more, heat transfer will be more. If A is less, heat transfer will be less. So this is just to get you an idea that for which shape and sizes TS will be more, and TS solidification time will be inversely proportional to thermal conductivity, directly proportional to this and also inversely proportional to thermal diffusivity, but it will be directly proportional to specific heat. Why it will be directly proportional to specific heat? Because if specific heat is more, that means you will have to take more times for solidification, and your metal will not solidify soon. So one more thing, solidification time of riser is greater than cavity because riser has to compensate for the shrinkages, hence it has to solidify later than the casting or primary cavity where the molten metal resides. And here V by A ratio of a cylinder, cube, elliptical cylinder, sphere, slab are shown, and also you can remember these things if you want, but the A here is total surface area and V will be the volume, and remember these two are the most commonly used. For cube, V by A is A by 6, and for this sphere it is D by 6 or R by 3. Rest you can look into once or twice, but these two you can remember them. So another note comes, solidification time is important in casting because it affects production rate, hence process economics, resulting microstructure, and hence properties. Choverinov's principle is having the solidification factor K, and the unit is second per meter square, and this K is depending upon metal and mold material first of all, and it is also depending upon density, heat capacity, and thermal conductivity. two cubical casting of the same metal of sizes 2 centimeter and 4 centimeter are molded in green sand. If the smaller casting solidifies in 2 minutes, expected time of solidification of large casting will be. Since this is first question that we are encountering from this principle, let's do it. So for smaller casting, let's take it TS1. It will be equal to K, same material. This is cubical casting, so A1 divided by 6 square, and it is given this side is 2 centimeter and the time is 2 minutes. So TS2, which will be the larger one of the cubes, equal to solidification factor A2 6, A2 will be now 4 centimeter, and don't forget the square here, and this will be how much you have to calculate. So here, since A2 is 2 times of this A1, so here it will be 2A1, and when we remove that 2 outside, take it outside, it will become 4. So 2 into 4, it will become 8 minutes. You can do this by other methods also, other calculation techniques also. So this C will be the answer. With solidification factor of 0.97 into 10 to the power 6 S by M square, the solidification time in seconds for a spherical casting of diameter 200 mm is, so it is TS is equal to K given in the question, diameter by 6, and we have to square it. So the correct answer will be coming out as, what is diameter given? 0.2, and we are going to take it in meter because K is given in S per meter square, divided by 6 square into 0.97 into 10 to the power 6, and we have to find this in seconds, so it is coming out as 1078, around this much, so that will be the correct answer. Volume of a cube of side L and volume of a sphere of radius R are equal. Both cube and sphere are solid and of same material. They are being cast. Ratio of solidification time of the cube to that of sphere. Again, simply you will take that TS is proportional to V by A square. Take that ratio, volume of these are equal, and I think you can get the answer very easily here. In sand casting process, a sphere and a cylinder of equal volume are separately cast from the sand molten metal under identical condition. Height and diameter of cylinder are equal. We have to find the ratio again. Same thing you have to do. Both the formulas you have to take here and get the answer. Easy question. Cube shaped casting solidifies in 5 minutes. Solidification time of in minute in cube casting of same material, which is 8 times heavier than the original casting. So here what you have to do, you have to take first find out what is the A2 and A1 relation is. So A2 is equal to how much of A1. So what is A2? Side of this second cube, and you can calculate this by using this. M2 is 8 times of M1, and rho 2, since this is cube, A2 cube will be rho 1 A1 cube into 8, and from here you can get A2 is equal to 2 times of A1. And now the same thing you can do, solidification time formula, and get the answer. Solidification time of a casting is proportional to V by A square. We know that V is the volume of casting, A is the total casting surface area losing heat. We also know that two cubes of same material and sizes are cast using sand casting process. The top face of one of the cubes is completely insulated. So since this is insulated, its A part will be having the value changed. Ratio of solidification time of cube with the top face insulated to that of other cube. So the top face of the cube is which is having the insulated, its solidification time will be more, because the area has been decreased. So it is now, the area that is losing heat is now decreased. So obviously your solidification time will increase. so it will be greater than 1, so it will be either this B or D. So let's look into what will be the answer. So TS, top face insulated, divided by TS normal will be, volume of both will be same, so it will be just getting cancelled out, and it will be just here our A divided by AI square. And what will be the area? The top face of this insulated one, which is getting insulated, will give this area as 5a square, since this is a cube, and it will be 6a square, and a squares will get cancelled out, and we will be left with this 6 square by 5 square, so 36 by 25 will be the answer. A cube and a sphere of made up of cast iron, where volume is given, where cast iron and this are cast under identical conditions. Time taken for solidifying the cube was 4 seconds. Time taken for the sphere we have to calculate. Again, same volume, so not that type of hard question. You can do this properly, easily, and I have done this as a matter of fact in my previous classes, so you can check that out. Ratio of solidification time of cylindrical casting, height is equal to radius, and we have to take that ratio of with a cubic casting of side 2 times of the height of the cylindrical casting. So again, same formula, use it. Some geometrical things you have to look into and get the answer. Solidification time of a metallic alloy casting is directly proportional to its surface area. No, it is inversely proportional to its A square. Inversely proportional to specific heat of the cast material. No, it is directly proportional to that. Inversely proportional to thermal diffusivity of the mold material. Yes. Inversely proportional to the pouring temperature. No, it will be directly proportional to it. So C will be the correct answer. And this question is very big lengthy question, but what this question is asking, let me just quickly give you a summary and then give you how to do this question, give you the approach. So there are thermal conductivities given of three materials: steel, copper and aluminium. Specific heats of them are given, and densities are given, and we know that solidification time is inversely proportional to thermal diffusivity, and this thermal diffusivity is K by rho Cp. So you have to calculate thermal diffusivity for steel, copper and aluminium, and whose thermal diffusivity will be this highest will be having solidification time least, and you have to arrange this in the increasing order of or in the from the fastest to slowest in solidification, that is in the decreasing order of how much fast speed is there, and or you can say in the increasing order of solidification time. You have to just write them down, select the answer. So this I was talking about this thing, thermal diffusivity, which is K by rho Cp. So high diffusivity means heat transfers rapidly. So if a high diffusivity is heat is transferred rapidly, then your solidification time will be reduced. It measures the ability of a material to conduct thermal energy relative to its ability to store thermal energy. And you can look into the definition and just know why it is said that K is the ability to conduct the thermal energy, and rho Cp can be taken as the ability to store thermal energy. A spherical drop of liquid metal having radius 4 mm solidifies in 6 seconds. What is the solidification time of the same drop with double radius? So we know the solidification time is proportional to V by A square, and it is proportional to D by 6 square. V by A will be for sphere, D by 6. So for 4 mm radius, it is having 6 seconds, and if the radius is getting doubled, so its solidification time will go 4 times. So it will become 24 seconds. So that was again it for the discussion here. Now let's look into what is left. So before our casting is going to get completed, we are left with this riser discussions. So let's look into that riser discussion. So for riser, we will have certain things to look here, and then we will see how to do some of the questions, and then end this discussion. We will also see what are chills and what are paddings before ending our casting discussion. So riser, we have discussed it. Riser is to compensate for liquid and solidification shrinkage in casting. It also provide an easy Risers also provide an easy exit for gases, and they eliminate the hydraulic ram effect. And why the hydraulic ram effect? Because when your filling is going to happen in the cavity, if there was no riser, then there will be sudden stoppage when the cavity gets completely filled. But if it is there, riser is there, the sudden stoppage is going to be just eliminated. So this hydraulic ram effect is eliminated due to riser. Riser provides extra metal pressure on the solidifying mold to produce exact mold details. So these are some of the functions of riser. And riser shape, here the two shapes are shown to you. So A by V is cooling characteristic. Rate of solidification of a metal varies directly with the ratio of surface area to volume. So surface area is least for this spherical shape. So riser will prefer this spherical shape because riser's main design needs to take care that it solidifies last or very after the casting, so that it can provide the molten metal to compensate for the shrinkages. So spherical shape is not usually manufactured easily, so we use this cylindrical riser design, which also does the same purpose, but it is not better than this spherical shape, but it is better than other shapes. So we have to just get this manufacturing easy also, and getting this advantage of having this solidification occur at a later time. So both of this are fulfilled by this cylindrical riser. Side riser and top riser are two types of riser. Side riser is having surface area exposed to heat transfer, which is complete surface area. So it will be for cylindrical side riser, it will be two times of the top and bottom cross section plus the curved surface area. And then we have a top riser, which is having only one of the cross section area and the curved surface area as the exposed area for heat transfer. The bottom surface area is not exposed because it is there in contact with the molten metal, not exposed to the this heat transfer, which is not exposed to the molding sand, so that heat transfer takes place. So this is obviously more effective because less surface area is exposed, so less heat transfer can occur through them. And optimum condition for side riser and top riser is shown in the table here. Optimum condition for side riser is when your height is going to become equal to diameter of that riser, and therefore your A by V ratio will come out to be 6 by D. For top riser, you are having the optimum condition as H equal to D by 2, and A by V will be similar, 6 by D. How we are coming to this optimum condition? We are taking the volume of the risers as constant, and then we are differentiating this area with respect to the diameter of the riser and taking this equal to 0. And we are doing this so that least surface area is obtained. So this equation, rate of change of area with respect to diameter equal to 0, gives us that least surface area condition, and that is shown in the screen in the table right now. So riser design is done by this three points. First of all, we are taking volume of riser as 3 into percentage of shrinkage volume of casting. And next we are if that is not going to give us a proper riser design, then what we are going to do, we are going to check if A by V for casting is greater than A by V of riser or not, because if it is not greater, then the riser will solidify soon, and hence our main purpose of making this riser, using this riser, is not fulfilled. So we need this B point to be satisfied. If B is not satisfied, then we can find the new dimension of riser using only this A by V and of casting, and equating this with the that of riser. So new H and D will be obtained from this. If with any of these points you can obtain that. Riser design: heat transfer can be minimized in riser by insulating material. We can provide that. Exothermic material, which is releasing heat so that it is keeping the riser warm. H is equal to D and H is equal to D by 2. That was the optimum condition for side riser and top riser. Blind riser. So top surface of the riser is also covered by molding sand in blind riser, as you can see in the figure. So heat losses less in blind riser when compared to open riser. Why? Because you can see it is having this whole thing covered with the molding sand, and this will account to less heat transfer losses. Now we have certain questions for riser, so let's look into them. So a casting is having this size, and we have to assume that shrinkage of casting as volume shrinkage of casting as 2.6 percentage. If the height of riser and the volume desired is 4 times in the casting, 4 times the shrinkage in the casting, what is the appropriate riser diameter? So it is going to be very easy calculation for this question. We will have to find first of all volume of riser, then we can find the diameter of that. So volume of riser will be 4 times shrinkage in casting. So that is coming out as 4 into shrinkage in casting will be 2.6 percentage of 100 150, that is volume of casting. So this will give us the answer as, that is volume of riser as 52,000. The units are mm cube, and we will equate this with the volume of riser, pi by 4 d square into h. Height is already given to us, so it will be, the diameter here can be calculated, and now the diameter will be, so diameter is coming out as of the riser 28.768, which will be 28.76 according to the options available. In mm it is given, so this will be our final answer, C. So a cylindrical blind riser, as you can see in the figure, with diameter d and height h, is placed on the top of the mold cavity of a closed type sand mold as shown in the figure. If the riser is of constant volume, then the rate of solidification in the riser is least when h is to d ratio is. So rate of solidification in the riser, we have to find that when this will be least. So here we have h shown and d also shown of riser, how the riser is looking like. And as you can see, the diameter is very much greater than the height. So we want, for the rate of solidification in the riser to be least, so we want the heat transfer to be occurring very much less, and for that we want more and more area to be not doing this heat transfer, and that will make the D more than H. So the correct answer, by that logic only, we can say that it is either A or C. So let's look what is the correct answer. So volume of riser will be And what will be the area of riser? So just what we have learned, del A by del D equal to 0, and volume is constant, we have to assume that. And here it is also given, so we can get the final answer. So first we have to do this, we have to, what we have to do, we have to take this area and put this, since h can also change, so we have to put that h in terms of d. What better way to do that by just than just doing, putting it in terms of d and v. I mean, v is constant, so it will be, and what will be h here? From here h will be v by pi d square and 4. We have to equate it equal to, and we have to make this equal to 0. So what we will see, first of all, pi's will be, or let's do the differentiation here. It will be 2d pi divided by 4 plus pi will be cancelled out. So 4v by d is left. So 4v by d square into minus 1 equal to 0. So we will do this here at the top. So it will be, since the digital pen was getting out of reach there, so let me just, so now it is fine. So what we have here is d pi by 2 plus 4v d square, not plus, here it should be equal to, because it was minus there. So here it is, we will take pi here and we can see that will make this term equal to h. So d by 2 is equal to, this will be h, and then we can have this, write this answer that we desire, that h is to d is coming out as 1 by 2. So just what we have learned, we have followed that and got this right answer. Riser design is also having this Keynes method. So for simple casting, freezing ratio is given as A by V casting divided by A by V of riser. So here this freezing ratio and this y, which is VR divided by VC, are in this relation that is shown here. X is equal to A divided by Y minus B plus C. You have to remember here X is freezing ratio, and the freezing ratio is defined as this. And also you can remember that freezing ratio is V by A of riser. You can write it like this also, and V by A of casting. And A, B, C are constant, which you can should be given when you are doing this type of question. And here if y-axis, which is VR by VC, and x-axis, which is freezing ratio, if your casting is in this region, if you calculated this values x and y and you find a point this, and your casting, therefore if it is in this region, then you can say it is sound casting. And in the bottom part of this curve, if it is there, then it is defective casting. Modified Keynes method, we have a surface factor, not surface factor, apologies for that, shape factor. So for complex casting, we use modified Keynes method, in which we use shape factor, which is length plus width of the casting divided by thickness. And same here, we have a curve above which we have sound casting, bottom part of that is defective casting. And here now the x-axis is your shape factor. So shape factor for cubes, sphere, cylinder and cuboid is shown in the screen. And let me just check one thing out, if I am missing something or not, that I have to here inform you about. So I have talked about this shape factor, modified Keynes method. So I think that will be it, because I can't find the. So I will look into that in the break, when we take a big break. So not big, 5 or 10 minutes break. I will look into that and inform you about if I was missing something here in the slides. Shape factor for a casting in the form of annular cylinder of outside diameter 30 centimeter, inside diameter 20 centimeter and height 30 centimeter is given. Correction factor is given 1. What will be the shape factor? So dimensions are given and we have to calculate shape factor. So shape factor will be L plus W divided by T. We have a annular cylinder. So for this annular cylinder, thickness will be can be easily calculated, d naught minus di divided by 2. What will be the length? It will be the height 30. And what will be the width? So width will be pi d average. So that is the perimeter. So perimeter will be width. If you just open the cylinder, you will find that as the width. So you will find a slab and that is the width. So that's will give you the answer to this question. So it will be, the average is 25 centimeter, or sorry for that Hindi words. So the average will be 25 centimeter. So pi into 25 plus 30 divided by, it will be 5. So the answer is coming out as 21.70 for mine. So it will be 21.77 as the answer. So we have a modulus method for simple casting. The again modified Kane method that we have talked about was for complex casting, but we have modulus method which is for simple casting. So modulus is given by V by A. So volume of casting or volume of riser divided by area, and MR, that is modulus of riser, should be equal to 1.2 of MC. That will make sure that your riser is solidifying after the casting. So you have this cylindrical job with 200 mm diameter and height 100 mm is to be cast given. And modulus method is used for riser design, also given in the question. Assume that the bottom surface of the cylindrical riser does not contribute as cooling surface. If the diameter of the riser is equal to its height, then the height of the riser is asked. So bottom part is not contributing in the riser as cooling surface, so that is similar to your top riser. So what we have to find here, we have to first find We have to find riser's height or riser's diameter because they both are equal, and we have been provided with these casting dimensions. So from a modulus method, it is mr is equal to 1.2 mc, and one is cylinder and other is also cylinder. So let's just calculate first of all this mc, which will be v by a for casting. So this casting is having this cylindrical shape, and the volume, first of all, it will be pi into 200 square divided by 4 into 100. Then we will have the total surface area, that is 2 into pi into 2.25 into 200 square plus pi into d into h. So it is coming out as 25, the volume here, or not volume, the modulus of casting here, and we have to multiply it by 1.2, that value, so that will be 30. And this 30 will be equal to mr, and mr will be equal to pi d cube by 4, because diameter and height are equal, and pi by 4 d square into 2, in not into 2 because one of the surfaces are not going to be involved in this, not going to be a cooling surface, plus pi d square. So here let's cancel out this pi's. We will be left with this d by 4, and here it will be 5 by 4. So we will be left with d by 5 for modulus of casting, and this will be equal to 30. And from here we can see that the diameter is coming out as 150 mm for, from this modulus method for riser. So it will be 150. Now the last thing, before that we will take a little break, and then we will see what chills and padding and other things we will do that, and then we will start the forming. And the next thing that we will do is welding. So again, a lot of things are left. So let's see. Directional solidification is the solidification that occurs from farthest end of the casting and works its way towards the sprue. So all grains are growing in single direction. This is what directional solidification is. So that will be it for the directional solidification. I hope this information is going to be useful for you. So let's take a break here, and let me bring my casting rest of the topics here to discuss. Then we will do the forming thing. So welcome back to the class after that break, which was much needed. We were going on for about quite some time. So let's continue the discussion that we were having. And I told to do some of the casting topics, but it looks like the casting topics that are left, that is chills, paddings, so they are used for directional certification. And that thing you can find in one of my previous recorded sessions, and I don't seem to find the PPTs for them right now at this moment. So I think we will move ahead with the other topics, and you for that you can watch the recorded sessions that already are present in the class or in this channel. So let me just open up that metal forming. We will start by cold working and hot working. So let me open that up. So let's start this cold working and hot working. We will do questions. We will not follow the same approach that we followed for the uh, casting. We will do questions and learn from this question. So let's discuss via this question. So first we have this question, what strain hardening does. So strain hardening, here the answer will be strength is going to get increased due to strain hardening. So what happens? Let's now discuss them. You have your grains which are something like this. Okay. So these grains, and I should draw them, remove this one. These grains, when they are getting this cold worked, okay, when you are going to do cold working, something's blocking me, which is causing this figure to be not properly drawn. So let's just draw it again. So when we are doing cold working of a workpiece, of a metal piece which is having this type of grains, so after cold working or due to cold working, this grains will become elongated and stressed. So this grains will become elongated and stressed when we do cold working, and due to strain hardening, this is going to happen, and this is going to be called as strain hardening. So when the grains are becoming this elongated in shape and having this more stress, so their strength, their yield strength will get increased and their ductility will get reduced. So when you will further try to decrease or try to just change their shape or size, you will find that you are getting more resistance than usual. That is due to its their strength is now increased. Again, strain hardening is the reason. In hot working processes, so after we have done all these questions, I think a lot of hot working and cold working things will be covered, and we will look if some important thing is left, and then we will talk about it, but I think a lot will be covered, which is important for gate. So in hot working process, metal is heated above a temperature known as, so that temperature is recrystallization temperature. So in hot working, we are working in at a temperature above recrystallization temperature. So at recrystallization temperature, what happens? New equiaxed, that is spherical, stress-free grains forms, and recrystallization temperature, or in hot working, at the end of your process you will get fine grains, because recrystallization has this grain refinement going on that will lead to them equiaxed, stress-free and fine grains. Deformation under conditions of temperature, strain rate, such that recovery take place simultaneously is with deformation is called as. So that is hot working, because in hot working we are encountering this recrystallization phenomena, and then in this recrystallization phenomena, what is happening is this recrystallization phenomena has recovery first of all. So all the stressed grains will become stress free, and new grains are also start forming. So strain rate recovery take place in hot working due to recrystallization, simple as that. Which of the following statement is or are correct for the cold working process? Strain hardening will take place in cold working, absolutely correct. In cold working process, recovery is not active. So that is also correct. Recovery is not active because there is no recovery. So both 1 and 2 are correct for cold working. Hot working does not produce strain hardening, correct, because their recovery is taking place, and recrystallization is also taking place. Hot working is done above recrystallization temperature. So since this is above done above recrystallization temperature, so it does not produce strain hardening. So that is the correct thing, and both A and R are correct, and R is the correct explanation of A. So A will be the correct answer. There is good grain refinement in hot working, absolutely correct, because recrystallization is taking place, and in recrystallization we find fine, equiaxed, stress-free grains. In hot working, physical properties are generally improved, so that is also correct, but R should be in place of A should be in place of R, so correct answer is B. Both A and R are true, but R is not correct explanation of A, it is the other way around. Specify the correct sequence. We first encounter stress relief or recovery, then we encounter recrystallization, then grain growth. So the correct is C, and this three things occur in annealing. So in annealing we encounter first of all stress relief or recovery phenomena, then recrystallization, then at last grain growth occurs, and therefore due to this reason, unlike in recrystallization where we find fine grains, here in annealing we are finding coarse grains. Hence, the ductility is even more than recrystallization and hot working, and therefore the material which is obtained, or the metal piece which is obtained after annealing, is softer. So its strength will also get some reduced. So if you want some proper strength and ductility, both go with recrystallization, because annealing will reduce strength and increase the ductility due to more than the recrystallization, due to the coarse grains forming due to this grain growth. Consider the following statements. When a metal or alloy is cold worked, it is worked below room temperature. So it is worked below recrystallization temperature. So 2 will be the correct. Strength and hardness increase. So it will be 2 and 3. In metals subjected to cold working, strain hardening effect is due to. So strain hardening effect in metal working when it is cold worked is due to dislocation. So due to this dislocation, we will have strain hardening. effect in cold working. In the metal forming process, the stresses encountered are greater than yield strength but less than the ultimate strength. We have to, this is talking about flow stress that you have studied about, that is greater than this yield strength but less than ultimate strength. What happens at yield strength? Just to remind you all, at yield strength, after this, or as we increase our strength and after it passes through this yield strength value, we will find the deformation as plastic deformation, and before this the deformation is elastic deformation, so recovery will take place. And at this ultimate strength, what happens? Fracture happens. So in metal forming we don't need to do fracture, we only need to do proper permanent deformation, that is plastic deformation. And for that, our flow stress or the stresses that are encountered in the metal forming processes are greater than yield strength but less than the ultimate strength. To obtain large deformation by cold working, intermediate annealing is not required. So it is required because annealing increases ductility and cold working decreases it. So we need ductility to be proper. So for this large deformations to occur, so A is absolutely wrong. So R will be true by default because that is was the option was given accordingly. So cold working is performed below recrystallization temperature of the work material. As I have said, it is correct. Cold working produces the following effects. Stresses are set up in the metal. So yes, grain structure gets distorted. Yes, strength and hardness of the metal are decreased. So no, they will be increased. Surface finish is reduced. No, surface finish will be increased in cold working. So 1 and 2 will be the correct answer. Cold forging results in improved quality due to which of the following? Better mechanical properties of the process? Yes. Unbroken grain flow, smoother finishes, high pressure. So which one of the followings are resulting in improved quality due to cold working? So in cold working, we will have better mechanical properties, that is for sure, and high pressure will be there. But high pressure is not resulting in this improving of the quality. So smoother surface finish, unbroken grain flow. So 1, 2, 3 will be the correct answer because for high pressure is still it is encountered in the cold working or cold forging process, but that is not resulting in the improvement of mechanical or properties or improvement of quality. So we will only select 1, 2, 3 here as the answer. Consider the following characteristics, and which of the following characteristic or above characteristic are hot workings. Porosity in the metal is largely eliminated. Strength is decreased. Close tolerance cannot be maintained. So close tolerance cannot be maintained, that is absolutely correct, but strength is increased due to recrystallization. So the correct answer here will be 1 and 2. That is I think, let's see here, 1 and 2 are not given, so it should be. So yes, close tolerance cannot be maintained, it is given. So 1 and 2 is the wrong answer. As I have said, strength will be increased. So say it correctly, but somehow. So this 2 will be wrong. So correct answer will be 1 and 3. Close tolerance cannot be maintained, and it should be increased here, and porosity is largely eliminated. So 1 and 3 is the correct answer. Which of the following is the process to refine the grains of metal after it has been distorted by hammering or cold working? We have annealing and recrystallization mainly to look here, and remember, as we have discussed, annealing's last step is grain growth and recrystallization is not having that grain growth. So recrystallization, after recrystallization we will have fine grains, and annealing we have coarse grains. So grain refinement is asked, so we will go with recrystallization or recrystallizing. So in this process In this question, the process which is followed, or the process which is used to refine the grains of the metal after it has been distorted by hammering or cold working, is recrystallizing or recrystallization. Materials after cold working are subjected to following process to relieve stresses. Now we are coming with annealing, because among these other processes, hot working is not a process to relieve stresses. It is annealing. Recrystallization can also do that, but hot working, no. Hot rolling of the mild steel is carried out. It should be above recrystallization temperature. Cold working of the steel is defined as working below its recrystallization temperature. A test specimen is stressed slightly beyond the yield point and then unloaded. Okay, now its yield strength. So since this is stressed slightly beyond the yield point, its yield strength will increase, because now its grains are getting deformed. Its grains are now stressed. So further deformation, when we will do, we will have to apply some extra stress to get that deformation done. So that was for cold working and hot working. I hope you have properly understood the things that I have talked about. And this cold working and hot working thing questions are properly covered. And if you have something, you can always go to my previous class and watch them. But since we have to cover this whole in this one session, so I'm moving in a fast pace. And if you have already studied this, you will find that this pace is very fine. So let's do the next question, next set of topics here, rolling. So let me open that slide. So let's start this rolling discussion. Then we, after rolling, we will do forging. Then we have extrusion and wire drawing. Then sheet metal, deep drawing, and some of the processes like spinning, the stretch forming, and we also have with to discuss bending. So this process and something other, we will also look what we are encountering, and mainly from questions we will discuss them. So after that we will talk about welding, but again that welding will be mainly focused, the main focus will be numerical sections. So we will look into them. We will look into the numericals, and we will discuss them, and then we will end this marathon session. So if the width of sheet is assumed to be constant before and after rolling process, then the velocity of sheet, so width of the sheet that is rolled is assumed to be constant before and after this rolling, and we we are asked what is the velocity. So in rolling process, you have thickness hi, width bi, and velocity vi. Then you have hf, final thickness, final width, and final velocity after your rolling has been completed. So rolling process will have this b change negligible. Okay, this width change will be negligible in this process. So it is also given in the question that it is assumed to be constant, so this is constant. After rolling process, and what happens, the thickness gets reduced. So to make this equation valid, if thickness is getting reduced after rolling, this will be increased, and this will be greater than this vi to make this equation valid. Okay, so Therefore, the velocity of sheet increases from entrance to exit. So that will be the B correct answer. And let me open. So let me open here the rolling process image for you to look. So this is the image, and let's reduce its size here. So here you can see that you have initial thickness of a sheet HI, and this initial thickness is greater than the final thickness HF. So this compression is taking place here when the rollers are compressing this to get its size reduced, and due to the volume of that is going in and coming out being equal, plastic deformation, and the width being constant due to negligible change in that, we are finding that the velocity initially V naught or Vi will be less than the velocity finally of the sheet. This is what rolling process this is what happens in rolling process, that this material or metal piece gets its size reduced due to plastic deformation when it passes through a set of rollers. A strip with cross section 15 or 150 mm into 4.5 mm is being rolled with 20% of area reduction using 450 mm diameter rolls. The angle subtended by the deformation zone at the roll center is in what radians? So that angle is calculated by cos alpha, and if you are new to this rolling, then you can remember this equation and solve this question. So this is the equation, and what is the angle? Let me show you here. So this, if is center, then you will find this angle alpha, which is, this is where the deformation is taking place, as you can see. So this is your deformation zone, or your contact length where the rollers and this sheet are coming in contact, and this is making an angle alpha at the center, and that angle we have to calculate, and that angle you can see where its derivation came from. But for the GATE exam, its derivation is not that important because it has not been asked yet, but still it is there in the syllabus, so you have to look into it. But here we will do just numerical. So cos alpha is equal to 1 minus delta h divided by d. We have delta h, that is reduction, and we have d also in the question given to us. So it will be 1 minus, what is reduction? 20% of the area, and here this is your width, which I have just told you it will be constant because of the negligible change, and this is your thickness. So the thickness will obviously get reduced as we have seen in the uh, rolling operation figure, and also as you have studied. So 20% of 4.5, what it will be? It will be 0.2 into 4.5, and what will be the diameter? It will be 45 or 450 mm. So we will get here, from here, alpha equal to, in radians we have to find that. So in radians it is coming out as 0.06325. So 0.06 should be fine. This is your bite angle or angle subtended by the deformation zone at the roll center in radians. In rolling operation, roll strip contact length is evaluated as delta H, that is change in thickness of the plate. This is also called draft, by the way. And R is the roll radius. So roll strip contact length L will be under root of R delta H. So that will be B option. And here this length, that is this length is your roll strip contact length when you take its projection in the horizontal plane. A steel plate 20 mm thick is to be rolled to 14 mm in 4 high mill having roll diameter 480 mm. If this yield stress is 120 megapascal, then angle of bite. So in this, yield strength is given, but we don't have to use that because angle of bite formula I have so this formula I have shown you, and similar formula, same formula we have to use here. So cos alpha is equal to 1 minus delta H, that is the reduction divided by diameter, and from here alpha will come out as so since it is to be calculated in degrees, it is coming out as 9.06 or 07, so 9.06 degrees. So correct answer will be A. So, to the students who are watching this live and you want the best Unacademy experience, then you have to visit their website and subscribe to them. A lot of quality crash courses and revision classes are going on there, which are taken by the Unacademy's top educator. So, to do that, and to subscribe and to get 10% discount, that is the extra discount, you can use this code ABHIMI. This code will give you this 10% extra discount, and now is the absolute right time, absolute perfect time for you to subscribe to Unacademy because of the revision classes that are going on, and also because there are test series that you have to give to finally prepare for GATE examination properly. So follow this basic steps or basic routine of attending a revision class or crash courses and then giving test series, and then just repeat this till your gate exam comes, so that you can prepare your level best. Okay, so this thing you can do to find yourself better prepared. So let's continue the things that we were discussing. In rolling operation, the maximum change in thickness of the plate is evaluated as so we have to answer that, and here the options which are given here: mu is coefficient of friction between roll and plate, and r is the roll radius. So remember, this is one of the formulas that I am going to get or make you revise by this question. So in rolling operation, the maximum change in thickness, that is delta H maximum or maximum draft, is given by this formula, mu square into R. So the correct answer will be D. And you have to remember, this is a formula. A steel plate 20 mm thick is to be rolled to 40 mm. So same data was given in one of the previous question. And if the given reduction is maximum reduction possible, then what will be the coefficient of friction? So the given reduction is 6 mm, and if it is maximum reduction possible, to calculate coefficient of friction, we have to just equate it equal to mu square r, and radius here will be 480 divided by 2. So mu can be calculated from here as 6 divided by 240 under root. It is coming out as 0.158. So that is option A. So 0.1581 it was coming, so option A is 0.158. We will select that. So that was the answer coming. In rolling process, the state of stress of the material undergoing deformation is. So here you see, this is the rolling process, and in this process you can clearly say that compression is going on because the metal is getting compressed. This thickness of it is getting reduced. But where the rollers and metal piece are coming in contact, there will be friction, and that friction will generate friction forces, and that friction forces will lead to shear stress, and that shear stress is very important in this rolling process. Why it is very important? Because that shear stress will help in unaided entry of this sheet or of this plate and make this pass through this roller gap and do this rolling operation unaided. So for unaided entry, friction is important, and that friction is causing the shear stress. So the state of stress of the material undergoing deformation will be compression plus shear. So C is the correct answer. At neutral plane, we find that the velocity of the sheet is same as velocity of roll. So that is some kind of a plane that you have in the sheet which is undergoing deformation, where velocity is same for sheet and roll. So velocity initially of the sheet will be less, after it will be more than the roller velocity, and at some point it will be equal. So that point is neutral plane. In a single pass rolling operation, a 400 mm wide steel strip having thickness 10 mm is reduced to 8 mm using a roll of 600 mm diameter. Determine the roll strip contact length. Also considering the situation for a maximum draft of the process. So what is draft? It is reduction. So draft is delta H. What is coefficient of friction? So roll strip contact length will be easily calculated. We have already learned about it. It will be R delta H, and coefficient of friction to calculate, we have to just put the delta H equal to this mu square R. This is maximum and it is assumed for maximum draft. So we can get the answer here by doing these things, and since only calculation is to be done here, so I'm not going to do that. I've provided you the formulas and how to use them. In a rolling process, sheet of 25 mm thickness is rolled to a 20 mm thickness and roll diameter is given and it rotates at 100 rpm. The roll strip contact length is asked. So same, r into delta h under root, you can find the roll strip contact length. And since this is very easy and only one part is asked, so let's do this very quickly. It will be 5 into 300 and we have to take this under root. So it is coming out as a 38.73. So it will be B. A 4 mm thick sheet is rolled with a 300 mm diameter rolls to reduce thickness without any change in width. Friction coefficient at work roll interface is 0.1. Minimum possible thickness of the sheet of that can be produced in a single pass. So minimum possible thickness is asked. So we have to find that maximum draft, then subtract it with the thickness of the sheet to find this answer. Again, not going to do this question. Very easy. Follow the basics formula that has been taught to you in this class and you can do that. But remember, you have been asked minimum possible thickness, not maximum possible draft. So you have to minus that maximum possible draft with 4 to get the answer. So don't just stop after calculating maximum possible draft. Thickness of a metallic sheet is reduced from an initial value to final value in single pass rolling with a pair of cylindrical rollers, each of diameter 400 mm. The bite angle in degrees is asked. Again, cos alpha is equal to 1 minus delta h by d. You can calculate it. Roll strip is to be or a strip is to be rolled from a thickness 30 mm to 15 mm using a high mill having rolls of diameter 300 mm. Coefficient of friction for unaided bite should nearly be. So this is a new question that we have not discussed formula yet in this class. So for unaided bite or unaided entry, this mu should be greater than or equal to tan alpha. And here we are not having this alpha, so we have to calculate it. So cos alpha will be equal to 1 minus delta h by d. So from here alpha will be equal to delta h is 15 and d is 300. So it is coming out as 18.2 degrees and tan alpha will be 0.328 or 0.33. So mu should be greater than or equal to 0.3286, which will be nearly this A approximately. So that will be the correct answer. Let me just review one thing before moving forward. So that will be fine. Let's continue what we were discussing. So I think if I took alpha there as 0 or 18.19, it should be, so still it is coming out 0.3286. so the correct answer will be A. It is coming near the answer that we require. So coefficient of friction should be greater than equal to tan alpha for this unaided entry or for this entry by friction itself. So that's it for rolling first part, but we also have to do another rolling question before we move forward and talk about forging, and that question is the calculation of force. So let me open that and then we will talk about how to calculate force for or how to calculate total power required for rolling operation. So let me open that. So this is the, so I hope the question is visible to you now. So this is the question that will cover our rolling power requirement calculation. So in a single pass rolling operation, a 20 mm thick plate with a width of 100 mm is reduced to 18 mm. The roller radius is given and the rotational speed is given. The average flow stress for the plate material is 300 megapascal, and the power required for the rolling operation in kilowatt is asked what value it will be closest to. So the power required for the rolling operation is asked, so we have to calculate the power required for both the rollers to make them do this process. So first of all, this is the formula for power. 2 into, we will look from the what we require from this formula. So 2t omega is how to calculate power, and omega can be calculated by 2 pi n by 60, so that is of non-issue because n is given and we just have to uh, convert that rpm into angular speed. But how to calculate torque? Torque will be, so torque here is calculated for one roller, that's why the 2 is there. So torque will be equal to rolling force F into arm length. And in this question, look here very carefully, there is not given this information whether this rolling operation is cold rolling or hot rolling. So we will take this by default, always take by default if something is not given about hot rolling or cold rolling, that is hot working or cold working, always take hot working. So arm length for hot working, A will be equal to 0.5 L, where L is roll strip contact length. So this is for hot working, and for cold working it is 0.45 L. We have to take this because by default hot working is assumed. And now how to calculate this F force? It is calculated by multiplying this average flow stress value into roll strip contact length into width, which will give us the value of this force. And how to calculate this roll strip contact length? It is equal to, as we have discussed, R delta H. So roll strip contact length, first of all, what it is coming, we have this reduction as 2 and radius as 250, so it will come as under root of 500, 22.36, and it will be in mm. The flow stress is given in megapascal, so we will multiply that with the mm square area to get the force in Newton. So that will come out as, what is width? 100. So it is coming out as 670,820.4 Newton. Now this is to be multiplied by arm length, which is 0.5 L, to get our torque, and this torque unit should be in Newton meter, so we will convert that arm length into meter. So this into under root of 500 into 0.5 will give us the value of arm length, but remember, value of this torque, but remember you have to convert the arm length into meter. So this 2 T omega will be equal to 2 into 7500 Newton meter into omega, which is 2 into pi into n, that is 10 divided by 60. So it is coming out as 15.708 kilowatt. So this is approximately or closest to A option. So our answer will be A, and here 2 multiplication is very important. So that is what we do to calculate the force that we encounter in the rolling operation, and also to calculate the power required for this rolling operation. So now let's talk about forging. So I will now open the forging PPT. So before starting this forging PPT, let's talk about forging by adding an image here. So forging process, in this we have two dies which are having this shape of the final product that we need, and we have a metal piece kept between these dies, and then we compress this dies, and the metal piece takes the shape of the cavities that are there in the die. And here this region that you are seeing, this region is flash. So flash is provided so that your proper filling inside the dies occur, because what happens when the die is making or being compressed and changing the shape of the metal piece, metal forming is being done when we compress this die. So this metal piece or this metal will have to flow to every corner of the die cavity, and that is made possible, or that is assisted by flash, because flash fills and solidifies faster, and hence it provides a pressure which helps in filling this metal piece and reaching this metal piece in the every corner of the die. So that is what flash is done doing. And another thing that here I will point out, this last part is your gutter, which is there, because sometimes if gutter is not provided, your flash will become very thick. So a region should be there where this excess metal will get accumulated, so that proper closing of die occurs. So how does flash assist in die filling? I hope you have now the answer. Increasing the pressure so that all the filling will be completed. It solidifies first or faster than the other parts of the metal piece when it is being compressed. So flash and gutter we have discussed here. Now we have this question. We have also discussed what basically forging is. So a forging method for reducing the diameter of a bar and in the process making it longer is termed as. So that forging method in which diameter is reduced and the length is increased is fullering. So punching and blanking are the sheet metal operation. Upsetting is in upsetting, what we do, we decrease the height and the cross section get reduced. But in fullering, and this is what a fullering operation looks like. So I will just add image to show you what fullerene looks like. So in fullerene, you can see here that the workpiece cross section or diameter is getting reduced and its length is getting increased due to its cross section getting reduced because plastic deformation, and perfectly plastic we have assumed it, so volume will be constant. So this operation is fullerene, and the reverse of this operation, that is just opposite, is edging. That is, in edging what happens, the metal piece is getting, the metals are getting accumulated at the center, and its center portion is having this higher cross section after the process edging. So this is also forging process, but here opposite thing is happening than your fullerene process. So this is edging. So I hope that two processes are clear to you. Now let's move forward and discuss the next question. Engineering strain of a mild steel sample is recorded as 0.1 percentage. True strain. So to calculate true strain, you have to do ln 1 plus engineering strain. But engineering strain here to be put without percentage. So without percentage, you will find 0.001. So your ln of this will be coming as, in percentage, if we have to provide the answer, we have to provide it by multiplying the answer with percentage. So this will be 0.099 percentage. So that is what your engineering strain is equal to, and also your engineering strain is equal to ln of initial area by final area. Also it is equal to ln of initial diameter square by final diameter square if the cross-sectional area is circular, and it is equal to final length by initial length. So that are some of the formulas that you can use to calculate true strain, and true stress can be calculated by using this formula. So you can also remember that, or if you already remember, just look into it and revise it. In open die forging, a disc of 200 mm diameter and height 600 mm is compressed without any barreling effect. So barreling effect is when your middle part of the workpiece get increased in area, and final diameter of the disc is 400 mm. True strain is asked. So true strain will be ln of initial diameter, which is 200 square divided by final diameter square. So we will have this 200 square divided by 400 square, and the log of this, natural log of this, is minus 1.386. So since in the option there is no minus given, the minus sign is representing that this strain is compressive strain. So the correct answer will be C, because in all the option there is no minus sign and it is matching with the value. So maybe the examiner has asked only the magnitude. So the correct answer will be C. The strain hardening exponent N of a stainless steel with distinct yield and ultimate tensile strength value undergoing a plastic deformation is, these are between this 0 and 1. When you do question, you can look into them and you will find them usually coming in this range. This N is between 0 1, and this N is equal to ultimate tensile strength's true strain. So that we will see in one of the question, that we will look into it. A solid cylinder of diameter 100 mm and height 50 mm is forged between two frictionless flat dies to a height of 25 mm. The percentage change in diameter is asked. So in this question, what will be the percentage change in diameter if so first we have to calculate the diameter, and since our volume will be constant, so we will just use this pi by 4 100 square into 50 equal to pi by 4 into d final square into 25. So from this d final will be coming out as, this will be 2, so 2 into 100 square, and it will come out as 141.42 mm, and percentage change in diameter is asked, so we will calculate df minus di divided by di into 100. So this will give us 41.42 percentage. So the correct answer here is coming out as D. Value of true strain produced in compressing a cylinder to half its original length. Now there are minus signs given, so we will have to select them if compression is going on, and since compression is what is given in the question, so minus sign should be expected in the question. So log of original length is L naught and final length is L naught by 2. So ln of half will be minus 0.69. So correct answer will be B. And this is true strain that we are calculating. True strain for a low carbon steel bar which is doubled. So doubled got doubled. So that is not the correct thing. It's by mistake. So true strain for a low carbon steel bar which is doubled in length for forging also got doubled here, is, so if the length is doubled, then we will find that it is 2L naught divided by L naught. So log 2 will be 0.69. So this will be, or 0.693 will be the answer. So this answer will be coming out as 0.693. So C is the correct answer, and this represents that the length is increasing. So tensile strain, we can see it here. The ultimate tensile strength of a material is 400 megapascals. The elongation up to maximum load is 35%. If the material obeys power law of hardening, then the true stress strain relation, where stress is in megapascal, in the plastic deformation range is to be given. So power law of strain hardening, I will write it here. Power law of strain hardening, this is given as sigma T is equal to K N. So we know that this is this sigma is true stress, this epsilon is true strain. We just have to calculate this K and N. So N is equal to true strain at ultimate tensile strength. So at ultimate tensile strength, we have the engineering strain as 0.35. So at ultimate tensile strength, epsilon is 0.35. So true strain will be ln of 1 plus 0.35. So this will come out as 0.30, and this is what is your N. So the correct answer will be one having this value as N, so A or B, and then we have to calculate this K, and always remember here sigma and epsilon T are to be written, not engineering stress and strain. So true stress will be 400 into 1.35, that is 540, and we have to divide that by engineering, not engineering strain, true strain raised to the power n. So true strain raised to the power n will be 0.3 raised to the power 0.3. So it will come out, the K will come out as, so this is what K was, and it was coming out as 775 megapascals. So the answer will be, in this power law of strain hardening, just put K and N, we will get the answer as B, that is the 775 epsilon, which is true strain raised to the power zero point 0.3. Now we have this match the following. In column 1, we have connecting rod, pressure vessels, machine tool bed, and collapsible tube. Welding, extrusion, forging, and casting are in column 2. So I should write this column 2. So connecting rods, pressure vessel, machine tool bed, collapsible tube. First we have machine tool bed. C will be for casting, more specifically sand casting, because sand casting have this advantage of unlimited size of object that can be manufactured or produced from that casting process, sand casting process. Collapsible tube, extrusion, and pressure vessels, welding. Then we are left with this connecting rods, which is forging. So here we are seeing A3, B1, C4, and D is 2. So B is the correct answer. So that will be it for forging, and my phone got discharged, so I will just connect it with charger so that I can see your questions that you are going to ask in the comment section. So I will be back after doing that. So charger is now connected, so I think we are ready to go now. So let's resume what we were discussing. So we have to start a new topic. We have completed the forging, we have completed rolling, we have completed cold working and hot working, and we have also completed this uh, casting process, which took a lot of time, by the way. And in the casting process, some things were left, but I didn't have right now the PPTs of that, and very few topics are left. Cast the chills and some of the riser topics little bit, and that you can find in my previous class, so I will not going to do them right here and take a lot of time. And also casting types have not been discussed in this class, that you and casting defects also, that you can find in one of my classes and attend that for as it is, as they are only going to be asked in match the following or a little bit of theoretical sections, and that are not that much frequently asked. So I think we should be going with discussing with the topics that are having a lot more chance of coming. So let's discuss